When you're walking on a street, let's say somebody comes to you and say, hey, electric potential at some point in space, let's call it point C, is 20 volt. What is the meaning of that statement? What would it mean? So by the end of the video, you'll be able to explain this statement in very simple terms to someone. To begin with, we are familiar with this word potential energy, and we've learned of potential energy when it comes to gravity. So let's start there. Say we held a 5 kilogram bowling ball in our hand, and I know bowling balls are a little larger than this, but imagine we held it at some distance from the ground, then we say that it has potential energy. Why do we say that? We say that because if I let go of that ball, then it's as it falls down, it's gonna speed up, and it's gonna gain kinetic energy. And we could ask, where did that kinetic energy come from? For example, let's say at this point we calculate and we figure out that the kinetic energy at this point is, I don't know, maybe 55 joules. And we don't have to worry about how to calculate that. Let's just take some random number. We could ask, hey, where did this 55 joules come from? Where was this before? Because energy can neither be created nor destroyed. And so we say, this 55 joules was already stored in the ball even before releasing it. And that energy is what we call potential energy. And so according to our example, this ball now has a potential energy, and the symbol we use for potential energy is usually U. And we say the potential energy of this ball is that same 55 joules. Okay? Now here's my question to you. My question is, a 5 kilogram ball held at this point has 55 joules. How much potential energy a 1 kilogram ball held at this same point have? Can you pause the video and think about this? All right, hopefully you've tried. So you might know that less mass means less potential energy. In fact, if I have only 1 kilogram, 1/5 of the mass, then even the potential energy would be just 1/5. And so 1/5 of 55 would be just 11 joules. All right. And so you know what I can do now? I can get rid of this ball, and I could say at this point, and I could put a indicator, I can label that point and say, let's call it point A, and I could say at this point, the potential energy is 11 joules per kilogram. That's how we can write. And what this means is if I were to keep 1 kilogram over here, it would have 11 joules of potential energy. And this number, how much potential energy you get per kilogram, is what we call potential. And we will write A over here because this is potential at point A and this is potential energy at point A. So do you see the difference between them? Potential is just potential energy that 1 kilogram would have. It's an indicator. Just like how when you go to grocery stores, you have indicators over there which says, hey, 100 rupees per kilogram. This means if you buy 1 kilogram, you pay 100 rupees, but it could also mean that if you buy 3 kilograms, you have to pay 300 rupees, and so on and so forth. Similarly, it's an indicator which says, hey, if you keep 1 kilogram, it would have 11 joules of potential energy, but you could keep 10 kilograms over here and it would have 110 joules of potential energy. So that's what gravitational potential is. So this is gravitational potential. Similarly, we can now define electric potential. So let me consider an electric potential case. So let's say we have something very similar. We have now a bowling ball which is charged because we want electricity. And let's say it has 20 coulombs of charge, a lot of charge. And let's say we have another huge charge which is negatively charged over here, somewhere down over here. And so now we have a situation which is very similar to that of gravity. If I were to let go of my hand, we know that that thing is going to get attracted towards this, and let's assume this is fixed then for simplicity, okay? And then it's going to get attracted and it's going to gain kinetic energy. And just like before, let's take some random number. Let's say that it gains a kinetic energy of, I don't know, maybe 100 joules. As an example, we could ask, hey, where did this 100 joules kinetic energy come from, right? And then we could say, that energy was already stored before. And we could now say that all that 100 joules was stored as potential energy. And I could now ask the same question as I did before. If 20 coulombs of charge at this point has 100 joules of potential energy, how much would 1 coulomb have at this point? What will be your answer? Well, just like before, it's going to be 100 divided by 20 coulomb. It'll be 1/20th of that. And so we can now write, we can now get, just like before, we can now get rid of that ball. I can put a label over there at that point, and I could say, at that point, the potential energy would be 100 divided by 20, that is 5 joules per coulomb. And this number is what we would call electric potential at point A. So now again, do you understand the difference between electric potential and electric potential energy? Potential energy, potential is just potential energy that 1 coulomb would have. It's an indicator. All right, so we can now define what electric potential is. Let me write that down over here. So in general, what is electric potential V, say at any point P? How do you define that? We could say that's the potential energy. Let's write that quickly. Potential energy, a 1 plus 1, we have to be careful about charges, so that it's positive or negative. You always consider plus as a standard. A plus 1 coulomb charge would have its potential energy per coulomb. And the way you calculate is you take the potential energy and you divide by the charge to calculate how much you get per coulomb. And the unit for that would be joules per coulomb. But it turns out that joules per coulomb is also called, because it's used so often, it's also called volt. Named after the physicist Alessandro Volta, who invented the very first battery. Okay, so volt is just joules per coulomb. And so now we can go back to our original question. If somebody says at some point C, just random point in space, that potential at point C is 20 volt. What is the meaning of this statement? Can you now explain this to someone? Pause the video and think. All right. We can now say, hey, first of all, volt is joules per coulomb. Remember that, and then you'll be fine. So we could say this means it's 20 joules per coulomb. And what it basically means, it's saying that if you were to keep 1 coulomb of charge at this point, it would have 20 joules of potential energy. But it's an indicator. So you can also mean that if you keep 10 coulombs of charge at this point, it would have 200 joules of potential energy. So remember, potentials are just indicators that we can add to any point in space. Now, of course, before winding up, I do want to mention that there are more than one ways to define electric potential. And maybe the most standard definitions are different, and we'll get to that. So we'll talk more about what does it mean to have negative potential energy or negative potential. What is potential difference? We'll get to all that fun stuff in the future videos. Just when I thought that I understood potentials, I saw weird statements like this. Electric potential at some point P equals negative 300 volts. And my brain was like, hey, what does that negative sign even mean? What does it mean to have negative energy? Well, by the end of this video, we will have a much deeper understanding of what electric potentials are, and we'll be able to understand what negative potentials mean. So just to quickly recall, what does it mean to say that potential at some point is 11 joules per kilogram? It just means that if I were to keep a 1 kilogram object over here, then that would have 11 joules of potential energy. But I could keep 10 kilogram object over here and it would have 110 joules of potential energy. It's an indicator. Similarly, what does it mean to say that at a point the potential is 5 volts? Well, 5 volts is just 5 joules per coulomb. And so that means that if I were to keep a coulomb of charge, let's say a rock which is positively charged for some reason, and let's say it's 1 coulomb, then it would have 5 joules of potential energy. But I could keep 100 coulomb of charge over here, and then it would have 500 joules of potential energy. It's an indicator of how much potential energy it would have per coulomb. And if you're not familiar with this concept or need a refresher, we've talked more about this in our previous videos on Introduction to Electric Potential. Feel free to go back and check that out. But let's dig a little deeper this time. Remember what does it even mean to say that potential energy of a kilogram is 11 joules? What does that number represent? Do you remember what does potential energy even mean? Well, we've talked about that. What this really means is that if I were to let go of this rock, let's say imagine I was holding that rock, and let's say I let go of that rock, then we know that rock is going to fall down, and as it falls down, its kinetic energy would increase. And this means that by the time it reaches the ground, all of that 11 joules is now converted into kinetic energy. That's what it means to have stored energy. That much can be converted to kinetic. And so this means when that rock comes from here to here, it would have lost all that 11 joules of potential energy. So do you know what we are really saying over here when we say VA is equal to 11 joules per kilogram? What we are really saying, and this is important, is that, let me write this down, is that if I were to call this point some other name, say B, then what we're really saying over here is that potential at this point is 11 joules per kilogram more than potential at this point. So let me just write that down and it'll make more sense as we talk more about this. So what I'm really saying is that potential at A is 11 joules per kilogram more than potential at B. This is what I'm really saying. Let me tell you why this is important. Now imagine instead of a ground, there was a table here somewhere. Now when I let go of this rock, it goes and hits the table and stops over there. And this time, by the time it reaches the table, do you think it would have gained 11 joules? No, it would have gained much less. Maybe only, I don't know, maybe only 3 joules of energy. Now what I would do is I would define the point over here. I would call this point as, say, I don't know, maybe T. And now I would say, hey, potential at point A is only 3 joules per kilogram compared to the potential at point T, because this is now a more convenient point to define potential. Depending upon which reference point we use, the potential at any point can change. In fact, there is no such thing as an absolute value of potential energy. The potential energy that you mentioned is always compared to potential energy at some other point in space. And to make sense of this, let me give you an example of something that you may be familiar with in maths, and that is a number line. If I asked you, hey, what's the position of this point? And I don't give you anything else on the number line, can you answer this question? No. You can only find positions relative to some other point. For example, you could say, hey, let me call this point as B. And now, if each one represents 1 centimeter, and to the right it's increasing, so we could now say, okay, 1, 2, 3, 4, 5. We can now say, hey, this point is 5 centimeters more than B. This is how we really represent in our number lines. And most often what we would say is this reference is often called the origin, and we call it 0. And as a result, now this would become 5 centimeter plus 0 would become 5. But what's important is I don't have to call that 0. Maybe I could call some other point as 0, and I could call this as, I don't know, maybe 10 centimeters. Then this automatically becomes 15 centimeters. So notice what the value, the actual position really depends upon what you call this position. All right, but what's important, what doesn't change is that this will always stay 5 centimeters more than point B. And similarly, somebody else could say, hey, you know what? No, I don't want to use this reference point. I want to use this reference point, and we can call this as T. Now, with respect to this reference point, what is the value of this position? It's now just 1 centimeter more, 1 centimeter more compared to T. And so now if somebody likes to call this as my 0, and then this would be 1 centimeter, and so on and so forth. Same idea over here. Potentials are always with respect to some other point. And the exact same thing happens in electric potential as well, exactly the same thing. And that's why I love gravity, okay? So when I say potential at some point A is 5 volts or 5 joules per coulomb, what I'm really saying is that, hey, it's 5 volt more compared to potential at some other point. some other reference point. In this case, I may have chosen this as my reference point. So long story short, potential or potential energy is always represented with respect to some other point. If I call the potential here as 0, then the value of potential here is 11. If I call potential here as 0, the value of the potential over here would be 3 in this example. And for gravity, we most likely always like to choose the lowest point in our experiment as 0 or as our reference point. But what about when it comes to charges? What's our convenient reference point over here? Well, the most convenient point we like to choose is infinity. So in any scenario, if the reference point is not mentioned and someone says, hey, potential at a point, let me just write that, potential at some point P is 30 volt. What does it mean if I don't mention in reference? It just means that it is 30 joules per coulomb. And that means that the coulomb over here would have 30 joules more potential energy than it would have at infinity. All right, so we always choose infinity as our reference point. So most of the time we like to choose this to be infinity, but it doesn't have to be, it's just a convenience. And so let me now show you a standard way of writing this. We often write this as potential at point A with respect to point B. That's how we like to write this. So this is my reference point, and we can call this as 5 volt directly. So this is the same thing as writing it this way. And you can also call this, so this would be just VA minus VB. So you can also write it this way. This also means the same thing. Potential at A, how much more it is compared to my reference point with respect to point B. And so this means whenever you're talking about potentials, you're always talking about the difference between the values of potentials between 2 points. And that's why we can also call this potential difference. So whether you call it potential at a point or potential difference between 2 points, it's really, really the same thing. And so now we can update our definition of potential. We could now say, hey, what does it mean to, what is the definition of potential at point P with respect to some reference point Q? We can now say, hey, it is basically potential energy that a charge would have at point P compared to at point Q per coulomb, per charge, okay? And this would be potential energy at point P minus the potential energy at point Q. You're basically calculating how much more potential energy it has compared to point Q divided by the charge Q. And for charges, most often this second point is taken to be infinity. So the second point is most often infinity. So I think we now have everything to answer our earlier question. What would it mean? So let me just, okay, there's no space over here. Let me go down. What would it mean if someone said, hey, potential at some random point P, electric potential was minus 300 volt? What is the meaning of this statement? Can you pause and try and explain this to someone now? All right, I would first say it is negative 300 voltage joules per coulomb. And what this now means is that potential at a point, if I kept a coulomb of charge at this point, it would have 300 joules of energy less compared to how much it would have at infinity, because our reference point is infinity. So now positives and negatives make a lot of sense because we are always comparing. If it's a positive potential, it's saying more potential energy compared to how much there would be at infinity. If it's a negative potential, we are saying, hey, less potential energy compared to at infinity. Just like in our number line, some positions can have negative values, meaning less value than our reference point, and some positions can have more values compared to our reference point. And finally, you can be even more curious and ask, hey, but how do we calculate the potential energy values in the first place? It's got something to do with work, and we'll explore all of that fun stuff in the future video. When charges are moving in electric fields, it can be quite confusing to figure out the signs of the work done. So let's solve a couple of conceptual problems to solidify their understanding. All right, so we are given a positive charge is moved slowly from P to Q. Find the sign of the work done by the electric field and by the external force in both the cases. So in both cases, we have one fixed charge, And then we are said, imagine a positive charge, another charge, is moved from P to Q. It's moved from P to Q in both these cases. And we need to find, in doing so, what is the sign of the work done. So we don't have to calculate anything. We just have to figure out what's the sign, whether it's positive or negative, of the work done by the electric field or the electric force and the external force. So how do we do this? So let me start with the first one. The first thing I'm looking at is it's moved slowly. And that's important. Why is that important? Well, I go back to gravity because I can always imagine things in terms of gravity. So think of it this way. If I had to, say, take this ball and move it slowly down, then what would I do? Well, I already know that gravity is going to pull on it downwards, and it's going to try and speed it up. To ensure that it doesn't quickly go down, to move it slowly, I will have to use my hand and say push it upwards. So what's important to see is that when you're moving things very slowly in a field, your force will always be in the opposite direction of the force due to that field. Does that make sense? Only then you can move it very slowly. If you put the force in the same direction, well, it's going to accelerate very fast. And so what that means, because what that tells me, is because our forces are in the opposite direction, that means when gravity does positive work, I do negative work. So for example, when the ball goes down, notice gravity is doing positive work, force and displacement in the same direction. And I would be doing negative work because my force is upwards and the displacement is in the downward direction. And similarly, say if I have to move this ball even further up, in that case, I would be doing positive work, the external force would be doing positive work, and gravity would be doing negative work. So what this means is that if I just know the sign of one of them, I would get the sign of the other. Okay, so all you have to do is imagine there's a positive charge at P, and you imagine moving it to Q, and you're just asking yourself whether you can either think in terms of the external force or electric force, whichever you want, and figuring out which one is doing positive work and the other one would be doing the negative work. So if you know one, you can get the other, okay? So why don't you pause the video and see if you can use this logic to figure this out. Don't use any formula, just try to do it logically. So start with this one, pause and try. All right, let's do this. So I'm gonna bring in a positive charge and I'm gonna keep it at point P. Oh, I've already placed it at point P, nice. So this is what we're gonna do. We're gonna move it from P to Q, and we have to think about whether the external force is doing positive work. Okay, basically science, right? So here's how I'm thinking. Just like I put forces over here, I'm gonna put force signs over here as well. So I know that electric field, the electric force is going to be in the opposite, it's going to be to the right. It's gonna get repelled by this charge, like charges repel each other. And so electric field is gonna put a force on it towards the right. Let me write that down. So electric field is gonna put a force this way. And so to move it slowly from here to here, my external force, external force has to go this way. I have to push it this way. And I also know that it's going from P to Q, so I have everything I need now. So it's going this way. Therefore, what is the sign of the work done by the external force, by me? Well, my force and the direction is in the same direction, and therefore I am doing positive work. So external force, work done by the external force is positive. But what about the work done by the electric force? Notice it's in the opposite direction. Notice electric force really wants it to go away, but it's coming in the other direction. So the electric force is doing negative work. All right, so does that make sense? Okay, why don't you try doing the same thing for the second problem? Pause the video and think about that. All right, let's do this. I'm gonna make a copy of my test charge and I'm gonna bring it over here. The question is the same, move it from P to Q. So I'm gonna keep it at P. And I'm gonna ask myself first, in which direction electric field is putting a force on this? So notice the negative charge pulls on a positive charge. Ooh, okay. So electric force this time is towards this charge. And therefore, my force has to be in the opposite direction. Notice, I will always put my force in the opposite direction. Otherwise, I will never be able to move it slowly. This is my force. Hope the color helps you recognize. Okay. And I'm moving it from P to Q just like before. So this charge is going from P to Q like this. And yeah, and now, what about the work done? What is the sign? Again, notice my force and the direction in which the charge would be traveling is the same. Therefore, again, I end up doing positive work. So external work is positive. And in fact, if you think about it, it makes sense. I can feel it, right? I can actually feel the charge. Separating the charge requires efforts. It's like separating magnets, stuck magnets. It requires efforts. So clearly I am doing positive work. I can feel that. And so electric force is doing negative work. Let's try one more. Similar setup, but we're given this time a negative charge is moved slowly from P to Q, and we have to find the sign of the work done by the electric field and the external force. So again, why don't you give this one a shot yourself first? All right, hopefully you've tried. So for the first one, again, I'm gonna do exact same thing, but this time it's a negative charge, but the concept stays the same. It won't matter. So here's my negative charge. Where is that? Okay, here it is. And we're moving it from P to Q. So I'm gonna keep it at P and we're gonna move it from P to Q. So the first thing I do is ask myself, hey, what direction are the forces? Because to find the sign of the work done, I need to know which direction the forces are, which direction the displacement is. So when I keep it over here, positive will attract. So the electric force is downwards. So I know that, downwards. And therefore, to move it slowly, my force should always be in the opposite direction. And I know it's being moved from P to Q, so I know it's going this way. So what direction, what's the sign of the external work? So my force and the displacement is in the same direction, so my work done is positive. So I do positive work. External is positive. What about the electric field? It ends up doing negative work. Electric does negative work. What about this one? Well, let's do the same thing. Let's copy it and keep it at P. That's where we're going to keep it. Okay. And again, I ask myself, what direction does the electric force act? Well, these are repelling each other, and so it'll move, try to make it move away, and therefore the electric force is this way. And therefore my force has to be in the opposite direction. And therefore, which direction is going? It's going from P to Q. It's P to Q. And one of the common confusions or common mistakes people usually make over here is, you think like this, or I used to always think like this, is, hey, I'm moving from P to Q, so my force must be downwards. It's not like that. Go back to gravity. Remember, even if I have to move this ball down, if I have to move it slowly, I have to keep pushing it up, even though I want that ball to go down. So yeah, it takes a little while to get used to it, because we usually tend to think that whichever direction you push, that object goes in that direction. But when multiple forces acting on it, you have to be a little bit careful. With a little bit of practice, you'll get it. Don't worry. Okay. So this time, notice electric force is doing positive work. So electric force is doing positive work, and I am doing negative work. And there we have it. We have solved. We now know how to figure out positive works and negative works and all of that thing. Potentials and potential energies can be so confusing. So let's try to solidify our understanding by solving a couple of conceptual problems. So here's problem number 1. We are given, or we are asked, find which point P or Q has higher electric potential. So we have two cases. In both cases, we have P and Q and we have charges. We need to figure out which point has a higher electric potential. How do I do that? So the first thing I do is I ask myself, hey, what's the meaning of potential? Well, you can think of electric potential as basically how much potential energy a coulomb would have at any point. So all I have to think about is when I take a coulomb of charge and I move it from one point to another, what happens to its potential energy? If it increases, then the potential increases. If it decreases, then the potential decreases. So that's all I have to do. But before I do that, I always like to go back and think from gravity perspective, because gravity helps me logically, because I have more experience with gravity than charges in my life. So just to remind ourselves, so that we make sense of this, in gravity also we define potential in a very similar way. If I imagine this is my test mass, all right? If I drop it, then I know as it goes down, its potential energy drops. And the reason we say that is because its kinetic energy picks up. So we say that potential is getting converted to kinetic. So the potential energy drops, and therefore I know as I go down, the potential also drops. So now all I have to do to figure out what happens over here is imagine a positive test charge. So here it is. And just keep it at one point and see if I let go of it, in which direction it moves. So along that direction, the potential must drop. So can you now use this and pause this video and see if you can figure this out yourself? So pause and try. All right. So let me keep it over here at point P. Let me start over there and see what happens. Well, if I let go of this charge, this repels this. And I know because of repulsion, and let's assume this is fixed. This is a very tiny charge, let's assume, okay? So due to repulsion, this starts moving away. Ooh, so that means if I were to keep it at point Q, it will automatically starts moving towards P. It will accelerate towards P. So that means, and let me write that over here, that means if I keep this positive charge over here, it will accelerate this way. It will accelerate in that direction, meaning it will pick up kinetic energy in that direction, meaning it should lose potential energy in that direction. And therefore I know that this must be high potential. So let me just write that down. Okay, this is high potential, and this side should be low potential. So over here, Q, the potential of Q should be higher than potential of P. All right, now before we go to the next one, and I know I'm pretty sure you are like motivated to go and excited to do the next one, I want to tell you that there are more than one ways to solve these things. And so I'm going to show you another way to think about it. If I go back to gravity, from this I can just see that along the direction of gravity, potential reduces. And that makes sense, because along the direction of gravity, body accelerates and loses potential. So if I just know what direction the field lines are, in that direction, the potential reduces. And so that's another way I can look at it. I can just say, let me draw field lines due to this positive charge, and along the field line, the potential would reduce. And we know that due to a positive charge, the field lines will always be away from it. So I can draw field lines like this. And notice, even I could have said this way, along the field line, potential reduces, and we get the same answer, high, low. Okay, how about you give it a shot for the second one? So pause the video, use the same logic, and see if you can figure out which has higher potential. All right, let's see. Let's do both methods. Let's first use the positive charge. Let's say I keep it at point P and see what happens. I let go of it, and I see it gets attracted by this negative charge. And again, we'll assume that the negative charge is fixed. This is a very tiny charge. So it gets attracted, meaning it accelerates this way. So let me write that down. So I know my charge is accelerating, accelerate this way. So it's kind of like falling towards Q, losing potential energy. So I know that this should have high potential, and this should have low potential. And remember, whenever you're doing this, you should always use a positive charge, because our potentials are always defined by positive charges, not negative. Okay, so this means VP over here is higher than VQ. And we can do the same, we can use the field lines as well. If I draw field lines for this charge, negative charges have field lines towards it. So field lines would be like this. And we just said, looking at gravity, along the field, potential reduces. Again, don't mug this up. Don't ever try to memorize anything. Always go back to gravity, it'll help. So along the field, potential reduces. High to low makes sense. All right, let's try another problem. A similar setup, but this time we're given if a small negative charge is moved from P to Q, what happens to its potential energy. So this time you have to move a negative charge from P to Q and see what happens to its potential energy. So again, why don't you pause the video and first give it a shot yourself. All right, hopefully you've tried. Let me start with problem A. I'm gonna this time bring in a negative charge and put it over here. So we have to move the negative charge from P to Q and see what's gonna happen. And we're gonna use the similar, very, very similar approach. If you want to know what happens to its potential energy, just let go of it and see which direction it accelerates. In that direction, it should be losing potential energy. Okay, so I'm gonna keep my negative charge over here at P, and I'm gonna move it from P to Q now. Okay, that's how I'm gonna do it. I'm gonna move it from P to Q and ask myself, as I move it from P to Q, what happens to its speed? Think of it that way. So let's see, if I keep it at point P, I know it's being attracted by this positive charge. And as a result, automatically it'll start moving, and it'll start accelerating. Its speed starts increasing. So let me just write that down. Let me write that down. All right, so I know that as it goes from here to here, it accelerates. And as a result, its speed must be increasing, kinetic energy must be increasing, therefore its potential energy must be decreasing. And so at this point, it must have high potential energy. So let me just write that over here. It should have high potential energy. And at this point, you should have, let me move this to the side. Okay. At this point, it should have low potential energy. So what happens? As it goes from P to Q, its potential energy drops. But before we move on, there could be some confusion based on what we did earlier. So if you looked at what we did earlier, what we found out earlier, we said as you go from here to here, potential drops, right? Like we said there is a field line over here like this, and then we said along the field line, the potential drops. So if I use a positive charge, then it's the exact opposite. We said this is high potential, and this is low potential, right? And this can be very confusing. What's going on? So think about it. When we talk about potential, electric potential, we are always thinking in terms of a positive charge. All right? So if you think in terms of a positive charge, it will accelerate this way, and as a result, you have high potential here and a low potential here. But a negative charge just does the opposite thing. It'll accelerate in the opposite direction. And so negative charges potential energy will be in the opposite direction. But if somebody asks you which point has a higher electric potential, you always think in terms of positive charge. And that's why the answer would be, in the previous case, what we got is this point is high and this point is low. And I know at first this could be very confusing, but remember, positive is your standard. So when people say what's electric potential, think from positive charges point of view, positive test charges point of view. And a negative test charge, if you were asked to do that, it'll have the opposite effect. The concept remains the same. And you may ask, okay, do I have examples like that in gravity? Unfortunately, no, because in gravity you only have positive masses. But you can think about a helium balloon. You can imagine a helium balloon, although it's not negative mass, you can kind of sort of think of it that way. And you can see a helium balloon naturally tends to accelerate upwards. And so it naturally accelerates from low potential to high potential, naturally, the opposite of what normal masses do, just like what we got over here. All right, so why don't you try using this for the second one and solving the second one? All right, let's see. So I'm gonna bring my negative test charge. I have to move it from P to Q and see what happens. So let's think about it. If I take this charge and move it from P to Q, what happens to its speed? Now notice it's being repelled by this charge. And so it automatically wants to go away. See, this charge wants to go away. But if I want to bring it from here to here, I have to like throw it. Sort of like when you take a ball, you have to throw it up if you want to go it up. upwards, right? So imagine I throw this charge from here to here. What happens to the speed of that charge? Ooh, it slows down, slows down, slows down, slows down, which means that kinetic energy is getting converted into potential, potential, potential. Ooh, let's write that down. Let's write that down. That's interesting. So if my negative charge were to go from P to Q, it will decelerate, not acceleration. It will decelerate. It'll slow down, meaning its potential energy should increase. All that kinetic gets converted to potential. And so I can now say, this should be low potential energy. It'll have low potential energy here. And as it goes over here, its potential energy picks up, picks up, picks up. And so it should have high potential energy here. And so what's the answer? What happens to its potential energy as it goes from here to here? It increases this time. It increases. And again, just like before, if I asked you what happens to the potential, electric potential as you go from here to here, then you have to think from a positive charges perspective, because positive is our standard. Then it will be the other way around. Just when I thought I understood positives and negative electric potentials, I looked at the textbook definition and my goodness, it had such big words like work done by external force, unit positive charge, infinity to that point without accelerating. And I was like, oh my God, what is this? This looks so different than what I understand. But in this video, we'll figure out exactly how we calculate electric potential using work done. And by the end of the video, this statement would have made a lot more sense to you. So let's quickly start with something that we've already seen before. In gravity, if I say potential at a point A with respect to its some reference is 11 joules per kilogram, it means if I were to keep a kilogram of rock, let's say at that point, it would have 11 joules of more potential energy compared to how much it would have at this reference point. Over here, it's the ground. And the same thing applies here. When I say potential at point A with respect to infinity is negative 300 joules per coulomb, it basically means if I were to keep a coulomb of charge over there, a coulomb of charge, let's say at that point, it would have 300 joules of potential energy less compared to when this is at infinity. And we've talked more about this in our previous videos on introduction to electric potentials and potential differences. So if you need a refresher, feel free to go back and check those out. But the goal of this video is to figure out how to calculate these values. How did we know this was positive 11, for example? And how did we know this was negative 300? How did we know it was negative? So how do you calculate these potentials? All right, so to do that, we can go back to our definition one more time. So potential at any point A with respect to some reference is basically how much potential energy that charge has at point A with respect to reference, which in our case is infinity, so compared to the reference per charge, because we are doing it for 1 coulomb. So I have to divide this per charge. And so all I have to do is figure out the potential energy difference. If I can do that, I can calculate the potential. So that brings us to the next question. How do we calculate potential energies? Well, I like to go back to my gravity. How do I calculate potential energy when it comes to gravity? I used to remember the formula mgh. It was very famous, but I don't want to do that. I want to use concept, basics, fundamentals. So how would I calculate, or what does it mean that my potential energy of 1 kilogram is 11 joules? What does it mean? Going back to basics, it basically means that 11 joules of energy is stored up. And if I were to let go of this stone, as it comes from here to the reference point, which is the ground, it loses all that 11 joules and it gains kinetic energy. So it gains 11 joules of kinetic energy, again, per kilogram, because we're defining it for 1 kilogram. So what I can say is, if I want to calculate potential energy at any point, just let go of that and see how much kinetic energy it gains when it reaches that reference point. Whatever kinetic energy it gained, that number itself should be potential energy, because that must have been stored up. Does that make sense? So let's write this down, because we'll do it step by step, slowly. So what I can say now is this number should equal how much kinetic energy was gained, or I'm just going to write gain, as it moved from A to reference point. As it moved from A to reference point per charge. So before we continue, let's just hold over here and see if we can use this definition to think about, to realize when we have potential, when the potential will be positive or negative. So when you go from your point, your preferred point to the reference point, if you gain kinetic energy, it'll be positive. And that's why we got over here positive number. As it went from here to here, it gained kinetic energy. But what if this number becomes negative? Then the potential would be negative. The example for that would be over here, if the reference point was above. Now think about it. Now when the rock is going from here to here, first of all, it doesn't automatically go. You might ask, how in gravity rock would go from here to here? How would it go up? Well, you imagine, you didn't drop it, but you imagine you threw it up. That's the trick. You imagine it's being thrown up. Now when it goes up, it slows down, it loses kinetic energy. And so this is negative. And therefore potential over here would be negative with respect to this point. Does that make sense? Pause the video and think about it, okay? Does it make sense to you? Well, yeah. Let's follow the chain of thought. As it goes up, kinetic energy is reducing, meaning potential energy is increasing. Therefore, this point has more potential compared to this. And so this point has less potential compared to this. And so that means this will be negative potential. So it makes sense, right? Same thing happens over here. Now, can you pause and convince yourself why over here we'll get a negative number? Pause and try. All right. If I were to let go, does it go to the reference point infinity automatically? No, it gets attracted. So I throw it away just like over here. And when I do, what happens to its kinetic energy? It reduces. Because it's of the attraction, it reduces. And if kinetic energy is reducing, you get a negative number here. That means the potential is negative. And see if it makes sense. Follow the chain of thought. If the kinetic energy is reducing, that means potential energy is increasing. So at infinity, you would have maximum potential energy. And so the potential energy over here would be less compared to that of infinity, giving you a negative sign. Okay, but now we can dig one step deeper and ask, hey, but how do you calculate this? How do we calculate how much energy, how much kinetic energy is gained or how much kinetic energy is lost? How do you calculate that? And for that, we use our work energy theorem, something that we may have learned a long time ago. Work energy theorem states work done equals gain in kinetic energy. So what I could write over here, the gain in the kinetic energy would be same as the work done by which force? The force of gravity here, or the force of electricity. So I'll just write force of electricity. Work done by the electric force in moving it from point A to the reference point. And again, per charge. And again, let's come back over here and see if it makes sense. So if I want to calculate how much potential energy I have over here, I need to figure out how much kinetic energy is gained or lost as it goes from here to here. But to do that, I have to calculate how much work gravity does in moving it from here to here. And how do you calculate the work done by gravity? Or how do you calculate work done by any force? You calculate it as the force multiplied by the displacement. So all you do is figure out how much the force of gravity would be. So maybe the force of gravity is downwards. Multiply that by the displacement, how much the displacement would be, and that number would tell you how much kinetic energy is gained, and that number would tell you how much potential you would have. And the same thing would apply here as well. If you want to calculate how much potential you have at this point, figure out how much work is done by the electric force. In this case, the electric force is downwards, but you move it all the way to infinity, so you have to move it in the opposite direction. So this is the electric force. And in doing that, figure out how much work is done. Now you might say, hey, but infinite distance means, is it infinite work? No, because remember over here things get a little complicated because as you go away, the force itself starts changing. And so you can't just multiply force and displacement, you'll have to integrate it. And something, don't worry, we'll not do this in this video, we'll do it in a future video, but you get the point. And notice over here, work done by electric force is negative as you go from here to here. And we already knew that because it's negative, we're gonna get a negative potential. Now, actually we are pretty much done because we now found a way to figure out potentials. All we have to do is calculate work done by the electric force in moving it from that point to infinity per charge, and we're done. But sometimes you will also have external forces acting on you. And so there's another way to define electric potential in terms of work done by the external force. Let me just introduce that because your textbooks tend to do that. It's not necessary. You don't have to do it. I don't usually use that at all, but let me do that anyways. Let me just define it anyways so that things are clear. Let me just get rid of this. All right. Imagine that when we're moving this rock from here to here, imagine we're not just dropping it. Let's say we are holding it in our hand and we are slowly moving it down. Slowly and steadily, without any acceleration, we are moving it down. Then my external force, the force that I'm putting on the rock, would be upwards. Let me write the external force with this color. Okay. This would be the direction of my external force. This would be my external force. Does it make sense? Because if it was not upwards, it would just fall down very quickly. I want to move it slowly without any acceleration. Then see what would happen. Then my force would exactly equal the gravitational force, but it will be exactly negative. And so the work that I did would be exactly negative of the work done by gravity. So I can also say, and the same thing would apply here. Okay, even here, what I could do is instead of throwing it and just allowing it to go slowly, what I could do is I could put an external force in the opposite direction, exactly equal to the electric force. This is the external force, and slowly, without any acceleration, move it from here to infinity. And in doing so, the work that I did would be exactly opposite of the work that electric field did. And so now I could also say that this is also equal to the negative of the work done by the external force in moving it from point A to the reference point. Does that make sense? Per charge. Per charge. Where is that? Okay, per charge. All right, but there's a caveat. There's a small detail. I have to move this without any acceleration. So conditions apply, no acceleration, because if I accelerate, let me show you. If I accelerate, then my force will not be equal to the electric force. Then my work done will not be equal to the work done by the electric force. Then this will not hold true. So only if I do it without acceleration, the two forces will be equal and opposite, and my work done would be exactly equal to the negative, but in number exactly equal to the electric force. So I can also use this definition. So I can also say potential at a point, I can also say it is the work done is a negative of the work done by the external force in moving it from that point to infinity without accelerating. Finally, what your textbooks do is they say, look, I don't want to define in terms of negative, so how do I get rid of the negative sign? And the way to get rid of negative sign is actually quite simple. See, if you do, when you are moving things down, if you're doing a negative work, then when you move things in the opposite direction, you will do positive work, right? So instead of moving it from A to R, you move it from R to A, and then the negative sign will go. So let me just write that down. We can also say this is equal to work done by the external force in moving it from R to A per charge. And I know it's a little crowded, so excuse me for that. And these two are the same things. And let's see what this means. This means, if I start with gravity because it'll make sense, it says if you want to calculate potential at any point A, find out how much work is done by an external force in moving it from ground to that point per kilogram. Does that make sense? Yeah. If I want to find out how much potential over here is, take a kilogram, move it from the reference point to that point A, and whatever work you did, that will be stored as potential. That makes sense, right? The same thing applies in the charges as well. And that's why your textbooks define it as potential at any point with respect to infinity. They don't mention that, but that's always with respect to infinity, equals the work done by the external force in moving a coulomb of charge from infinity to that point without any acceleration. And now I know there is a lot of things introduced, so it's going to take some practice to get used to it, but we now have so many different ways of calculating potentials. My favorite is just doing this. This is literally my favorite. This is the easiest. I don't have to worry about external forces, but yeah, you can use these definitions as well. Imagine we have an electric dipole, basically negative charge and a positive charge of same value, separated by some distance. Let's say we call it 2a. Traditionally, we call that 2a. Our goal is to figure out what the potential due to this dipole is going to be at some point P. Let me write that, show that at some point P far away from that dipole, at some distance r far away. These dotted lines are showing far away. And just to show you the real picture, this is what it would look like if I were to actually show you this to scale. Imagine it this way, that this distance r is way bigger compared to a. That's what I mean when I say I want to calculate the distance potential very far away. All right, so let me just keep this picture somewhere over here. Now the question is, how do I do that? Well, I already know how to calculate potential due to a point charge. We've seen the expression for that. It's kq 1/4 pi epsilon naught, which is called k. So kq divided by r. So all I have to do is figure out what's the potential due to this charge over here, what's the potential due to this charge over there, and then just add them up. But you could say, hey, the problem is I don't know what's the distance of that point P from this charge and from this charge. That r is a distance from the center. So what is this distance and what is this distance? That's not given to me. So what I'll do is, like in most cases in physics, when something is not given, well, you draw that and you assume something. So let's do that. So I'm gonna draw some lines from here. Let's call this distance from here to here, let's call that R1. So this is my R1. And from here to here, let's call that distance to be R2. And now in terms of R1 and R2, we can write down what the electric potential is going to be. It's due to this plus due to this. So can you pause the video and write down what the expression for the electric potential P turns out to be in terms of R1, R2, Q, and minus Q? Pause the video and give it a shot. All right, let's do this. So the electric potential at point P is going to be the potential due to a positive Q at point P plus the potential due to negative Q. You might be thinking, hey, there's a negative sign, right? Well, the negative sign comes here itself when I substitute. All right, so if I do that, if I substitute, due to plus Q, it's going to be KQ divided by R2, so R2. And you will have, due to the negative Q, you'll have minus KQ, the minus sign comes from the negative charge here, divided by R1. Divided by R1. And we're done. Now comes the question, what do I do further? This is not done because we have to find out the expression in terms of R that's given to us, not R1 and R2. So what do I do is the question. Well, I know the condition is going far away. And what that means is that this distance R is way bigger than that distance 2a. So let me write that down. So that's our condition. So we are calculating this far away. And we're doing that. What does that mean? That means that this distance R is way bigger than this distance 2a or a, whatever you want to call that. Okay. So how do I bake this in over here? How can I use this to somehow simplify this? Well, when R is very far away, something very interesting happens when you compare R1, R2, and R. Let me show you. Let me draw R1 and R2 here also. And you will see something really interesting. What you now find is that the length of all the three lines are almost equal to each other. Can you see that? Because P is so far away, this looks like almost a point. These three lines will almost have the same value, which means because it is far away, I can now say this means R1 is almost equal to R2, which is almost equal to R. Okay, they're almost equal. So now comes the question, what do I do? Can I somehow use this over here? And my first thought would be, since we want an approximate value, let me just go ahead and substitute and see what happens. And why don't you give it a shot? You don't have to actually, you can do it in your head. What will happen if I substitute R1 as R and R2 also as R? What will I get? Substitute and see. Okay, If I put both of them, the denominators become same, numerators are also same. When I subtract, I'll get 0. So let me just write that down. If I were to directly substitute, so direct substitution, what does that give me? We get potential at point P to be 0. And that is wrong. Why is that wrong? Why can't that be an approximate value? Because although they are approximately equal to each other, I know from the diagram, I can see that R1 is slightly bigger than R2, slightly bigger than R2. Q plus Q is slightly closer compared to minus Q. Therefore, the potential over here must be slightly positive. So there is some slight small value which is not 0, and my goal is to figure out the expression for that small value. Are you getting that? Okay. So how do I figure that out? How do I figure out that expression for that small value that you're gonna get? So what I learned whenever I'm doing this is, if direct substitution doesn't work, you simplify that one more step, let's say, and then try substituting and see what happens. So let's go ahead and simplify this. Now this is no longer physics, we're just doing algebra, simplifying. I can take common denominator, so let me go ahead and do that. So if I take the common denominator, I get Vp to be equal to, let's see, I can take KQ out. And when I take common denominator, I get R1 minus R2. So I get R1 minus R2 divided by R1 times R2. So that's going to be R1 times R2. And now let's see if we can substitute this over here and see what we get. If I were to substitute in the denominator, R1 is R and R2 also is R, I will get R squared. R into R is R squared, and I don't get 0. So yeah, I can substitute that in the denominator. So what I'll do is, in the denominator, I'll call this R squared. And what about in the numerator? If I call this R and if I call that R, now R minus R is 0, and again I'll get this as 0, and so I can't substitute. So in the numerator, I will not substitute. And at this point, I'm sure you may be thinking, what is this business of somewhere you will substitute and sometimes you will not substitute? What is this? What is going on? So let me walk you through this. It took me some time to realize, but now finally I understand what's going on. So let me take some numbers. It'll make sense. So imagine R1 was, say, 11. And let's say R2 was a little smaller. So let's call that 9. And let's say R, somewhere in between the two numbers, is 10. Okay, let's write that down over here as to what happens when you approximate. So what is the actual value? What is the real value? Well, that is 11 times 9, that's 99. And what's our approximation in this case? It's 10 square, which is 100. And so what's the error, we can say, right? When you approximate, you get an error. So what's the error over here? The error is 1. There's a difference of 1, positive 1, but it's okay, you get 1. And compare the error with the real value. It's 1 out of 99. So it's almost like saying 1 out of 100, so it's 1% error. So we're saying this equation, this is 1% wrong with these values. And I can say I'm okay with 1% wrong, no problem for me. But now let's do the same thing for the numerator and see what happens. So what is the real value if I were to substitute the values over here? 11 minus 9 is 2. So this is 2 in the numerator. What if I substitute 10 here and here? I get 0. That's the approximate value. What's the error? The error is also 2. Now 2 out of 2 is 2 divided by 2 is 1. That's 100% error. And that's not acceptable. So if I were to approximate over here, I'm getting 100% wrong answer. And I don't know about you, but I don't want to get 100% wrong answer. So when you get 0, you end up getting 100% wrong answer. So 100% error. And that's why we can't substitute in the numerator, but we can substitute in the denominator. And pause this if it didn't make a lot of sense. It didn't make a lot of sense to me initially as well. Take some time to soak in, take some time to digest that. So pause and then we can continue. All right, let's continue. So we are now reached an interesting point, very, very interesting point, and an important point in this derivation as well, where we need to find what the difference between R1 and R2 is. We need to find that under the condition that they're almost equal to each other. Okay, how do you do that? How do you say that they're almost equal to each other and somehow find the difference between the two? Now there are multiple ways to do that, but the way I like to do it is zoom in on this real picture. Zoom in, zoom in, zoom in, go close to my dipole, and you notice something. you notice that if the point P is very far away, then all these three lines look parallel to each other. And that's the secret we're going to use. Look at them. They look so parallel to each other. So I'm going to go back, I'm going to redraw this, and this time I'm going to draw R1 and R2 parallel to each other. And the point P is really, really far away. So how does that help us in figuring out what this is? Well, remember, what I need to figure out is the difference between these two lines. And one of the ways to calculate the difference between two lines which are parallel to each other in this case would be, let me show you, to drop a perpendicular from the shorter line onto the bigger line. So let me try that one more time. All right, there you go. So this is a perpendicular and this is a perpendicular. You may ask, how does that help? Well, it helps because now, if I call this point as something else, the point P is at the same distance from here to here. From here to P and here to P, distance is the same, which means that extra distance, R1 minus R2, is this. Let me just quickly write that down. This is that extra R1 minus R2. So that is our delta R. And if you're wondering why does it work out that way? Well, look at this picture. When I draw that perpendicular, which you cannot see properly, let me zoom in a little bit. Okay. When I draw that perpendicular, notice we end up with a giant triangle. And in that triangle, this angle is almost 0. And these two angles are almost 90 degrees. Okay, you may be wondering, how can you have a triangle like that? Well, think of it as 89.99, 89.99, and 0.00001 or something like that, okay? So look at that triangle. These triangles are equal. That means this is an isosceles triangle. And as a result, this side is exactly equal to this side. And therefore, that extra distance should be R1 minus R2. So this should be R2. So this should be R1 minus R2. Does that make sense? So this is that extra distance. Okay. Now, the final question we have is, what does that extra distance really depend on? And if you look carefully, you can see that that really depends upon the angle between this R and the dipole. Let me show you that. I have an animation over here. Let me show you. So here you go. This is our delta R. And notice what happens as this angle decreases and this point P comes on the equator. Oh, sorry, on the axis. Notice what happens. Look at that, look at that, look at that. Can you see? When the point comes on the axis, hopefully you can see that R1 minus R2, delta R, automatically becomes 2A, maximum. All right, notice what happens as this now comes off this particular axis and comes back. What happens? This will become smaller and smaller and smaller. And if it now comes somewhere over here, notice, eventually becomes even smaller. And finally, when that point P is right in between these two, that difference becomes 0, which makes sense, right? If that point P is right in between these two, distance from here to P and here to there would be 0, would be equal. And so there will be no difference. So hopefully we can see that, let me get rid of this, that this delta R depends on this angle. And so let's bake that angle in. So let's call that angle as theta. Okay. And so if that angle is theta, we are assuming that all lines are parallel. This angle also becomes theta. And so now comes the question, using theta and using this right angle triangle, can you figure out what delta R is going to be from this? I'm gonna give you a clue. It has trigonometry. So pause the video and see. Final pause. This is the final part. All right. So in this triangle, notice 2A is the hypotenuse, and this, but what we need is the adjacent side. So I'm going to use cos theta. So from here, I can say cos theta equals delta R divided by 2A. And so what is delta R? So I can substitute that directly over here. This is our delta R, okay? So what is delta R? Delta R is just 2A cos theta. Let me write that. Delta R equals 2A cos theta. And so if I substitute that, I now have my final equation. So VP is going to be KQ into 2A cos theta, 2A cos theta divided by R square. And that is our expression for the electric potential due to a dipole. And so what you notice is that the potential due to a dipole not only depends on the charge, but also depends upon the distance between the two charges. Not so surprising because we've seen that before when it comes to electric field as well. And so this is what we call, the product is what we call the dipole moment. But notice here, we also see that its dependence on this angle theta. And we saw why that is the case, because this R1 minus R2, the difference between the two, that depends on that angle. And so the most important step over here was to figure this out in the limit that R1 is almost equal to R2. And the trick was to imagine that assume that they are parallel to each other and use trigonometry. Let's work out some numericals on electric potential due to dipoles. So here's the first one. We are given a dipole, there's a point dipole, tiny dipole, whose moment is given to be 3 times 10 to the minus 8 coulomb meter. This is not centimeter, this is coulomb meter. And we are asked to calculate what the potential is going to be at distance of 2 meters from that dipole along the axis. So how do we do this? Well, in a previous video, we already derived what the expression for the potential due to a dipole anywhere is. So let me quickly show you that. We saw that if you have a dipole, let's say there's a negative charge, there's a positive charge, separated by some distance we used to call 2a. And if you want to know what the potential at some point P at a distance r from the center of the dipole, then we saw that that expression is going to be k q into 2a cos theta, where theta is this angle, theta, divided by r squared. And how did we derive that? Well, we calculate what the potential here is going to be due to this charge, potential here is going to be due to this charge. We added them, and then we did some mathematics where we said, okay, let's assume that P is to be very, very far away. And if you need some clarity or you need a refresher on how did we derive that, where does it all come from, it'd be a great idea to pause this video. It'll be a great idea to go back and watch our video on the derivation of electric potential due to dipoles. But anyways, let's continue. What's given to us is we're not given q, we're not given the distance, we're given the dipole moment, and we're given some vector. What is that? Well, remember that this product itself is what we call this product of charge and the distance. That itself is what we call the dipole moment, which we represent as P. And what does that direction say? The dipole moment is taken to be a vector, and its direction is always from the negative charge to the positive charge. So this is your negative charge, this has got to be your positive charge. So in here, dipole moment is this way. Okay, and so to think about that angle, the theta is the angle between the dipole moment vector and the vector that points towards P, the r vector and the dipole moment vector. That's our angle. All right, so why don't you pause the video and see with this now, can you go ahead and solve this particular problem? All right, so let's do this. So what is k? K is that familiar 1 over 4 pi epsilon naught, whose value is 9 times 10 to the power 9. And I don't know the charge or 2a, but I know the total product, that's dipole moment, that's given to me as 3 times 10 to the power minus 8. And what is cos theta over here? What is theta? Well, theta is this angle. In our case, notice, if I were to draw that vector from here to here, that angle is 0. The two are aligned, so cos 0, so let me write that, cos 0 divided by r square. R is this distance, 2 meters. So 2 square is 4. And it's in meters, so I don't have to do any conversion. And therefore, all I have to do now is solve this. So I get cos 0 is 1. So this will be 27. This will be 10 divided by 4. So that's 270 by 4. That gives me 4 6 are 24, 3 carries 30, 4 7s are 28, 2.5. And there you have it. 67.5 volt. That's the potential here. We're getting a positive sign. Does that make sense? It's positive? Yeah, because the point is closer to the positive charge and a little farther away from the negative charge, so it makes sense that we're getting a positive voltage. Let's try a second one. Again, we are given a dipole. This time we have charges given, the distance between the dipole is given. We have to find the potential at point P at a distance 10 meters from the dipole. And again, notice that this is a point dipole. This distance is much smaller compared to this, so we can use the far away approximation, the same thing that we did here. So again, can you pause the video and try solving this one on your own? All right, let's do this. So we'll just substitute this value. So you get Vp is equal to K is 1 pi 4 pi epsilon naught. That's 9 times 10 to the power 9. Q is the charge that's given. And remember, we just have to calculate, put in the magnitude of the charge. The sign is already baked in when we derive the formula. So just the magnitude. So 3 times 10 to the power minus 6. Minus 6 because it's a micro. Micro is 10 to the minus 6. And times 2a. Now, one of the mistakes I used to make while substituting over here is 2a, I used to put 2 times, say, 1 millimeter, but it's not. This itself is 2a. Remember, 2a is the distance between the two charges, okay? So 1 millimeter itself is my 2a. So it's 1, and a milli is 10 to the minus 3. So let's take care of our 10 powers. Times cos theta. What is cos theta? Well, there's a 60, so we might write cos 60. That's wrong. It's not cos 60. Can you pause and think a little bit about why it's not cos 60? All right, let's see. What is theta again? Remember, theta is the angle between the dipole moment vector, which starts from negative charge to the positive charge, and the r vector. So over here, what is our dipole moment vector? So dipole moment vector is from negative charge to the positive charge. It's downwards this way. This is our dipole moment vector, and our r vector is this way towards P. And so notice the angle theta is this angle, and that's not 60. The whole angle is 180, so this is 180 minus 60. So that's our theta, 180 minus 60. So let's correct that. So that gives us 180. I can just write 120, but I like to calculate this way using our what do you call it? Allied angles? Yeah, allied angles. I think that's the term. But anyways, so divided by r square. What is r? R is 10 meters, so it's gonna be 10 square. That's 100. So let's see. We just now have to plug in. So 9 times 3 is 27. Times this, and this cancels out. See, 10 to the power 9 minus 6 minus 3 minus 9. That nicely cancels out. What is cos of 180 minus 60? Well, I remember the allied angles thing. If cos of 180 minus theta is, since this is in the second quadrant, I write A, S, T, C. So in second quadrant, cos is negative. So it's going to be minus cos 60. So this is going to be minus cos 60. And cos 60 is half, so I'll get minus half over here. Divide by 100. And that's going to be 27 by 2, which is, what is that? 18.6. No, 13.5. So it's negative 13.5 divided by 100. So that's minus 0.135 volt. And so let's think about, does it make sense that we're getting a negative sign over here? Yeah, because this time notice that point P is a little closer to the negative charge compared to the positive charge. So even if we had wrongly substituted this as cos 60 and gotten a positive value, we could just look over here and say, hey, that's supposed to be negative. And then I could have like realized why am I getting a positive value, and I could have gone back and corrected myself. We've learned how to visualize electric field by drawing field lines. In this video, let's explore how to visualize electric potentials. And the way to do that, or at least one way of doing that, is by drawing something called equipotential surfaces. So what exactly are these? Well, as the name suggests, these are surfaces, and these are three-dimensional surfaces over which the potential at every point is equal. Equipotential surfaces. So let me give you an example. So if we come over here, let's say from this charge I go about 2 centimeters far away over here. There will be some potential at that point. Let's call that as 10 volt. Let's imagine that to be 10 volt. Now, if I went 2 centimeters over here from the charge, what would the potential there? There should also be 10 volts. What about 2 centimeters from here? That should also be 10 volt. In fact, I could draw a circle of 2 centimeters, and 2 centimeters is just an example, okay? And everywhere on that circle, the potential would be equal, 10 volt. So that circle would be an equipotential surface. And since it's a three-dimensional, you have to imagine this actually is not a circle, but it's a sphere. So let me just draw that nicely. So I could draw a sphere. Let's see, here it is. A sphere, and you have to imagine this is a three-dimensional sphere, where on every point of it, the potential is 10 volt, equal. And so this would be my 10 volt equipotential surface. Can I draw more? Of course. If I go a little farther away, maybe 2.5 or 3 centimeters far away, can draw another sphere that will have that would be another equipotential surface. Let me draw that. If I go farther away, the potential will decrease, right? So let's say this is another equipotential surface. Why is this equipotential? Because on every point of it, the potential is equal, and it's equal to 7 volt. Can I draw more? Yes, more spheres. Every sphere you draw will be an equipotential surface. In fact, if I go a little farther away and I draw another one, I might get a 9 volt equipotential surface. If I go a little farther away and I draw another one, I might get an 8 volt equipotential surface, and so on and so forth. Now, before we continue, you may immediately notice that the surfaces are closer here and they're going farther and farther away. Why is that? Well, it's got something to do with the strength of the electric field. Close to the charge, the field is very strong, and that's where the equipotential surfaces would be closer to each other. As we go far away from the charge, the field weakens, and so the surfaces go farther and farther away from each other. But why? Why is it that if the field becomes weaker, the equipotential surfaces go farther away? Can you pause and think a little bit about this? All right, here's how I like to think about it. Consider a tiny test charge kept over here on the 10 volt equipotential surface. What will happen if I let go of it? Well, the electric field will push it and it will accelerate and it will move from this equipotential to another, the 9 volt equipotential. Now, because the force over here is very strong, because you are in the strong electric field region, it will accelerate very quickly. It will gain kinetic energy very quickly. And as a result, it will lose potential energy very quickly. And it's for that reason, in a very short distance, it would have reached from 10 volt to 9 volt equipotential surface. However, what would happen if I were to keep that same test charge over here? Well, now the field is very weak, or weaker compared to here, and so the force acting on it is very weak, and so it will accelerate slowly. And so it's going to take more distance for it to pick up the kinetic energy. And so it's going to lose potential energy more slowly. And as a result, it's going to take a longer distance before it loses 1 volt now. And so what do you think will happen for the 6 volt equipotential? It will take even larger distance to reach 6 volt. And so it'll be even farther away. Does that make sense? It's kind of like if you take a ball and drop it on, say, Jupiter, where the gravitational field is very strong, then it will accelerate very quickly, and so it will gain kinetic energy very quickly, so it will lose potential energy very quickly. But on the other hand, if you were to drop that same bowling ball on, say, Moon, well, because the gravitational field is very weak, it's going to accelerate very slowly, gain kinetic energy very slowly, and so therefore lose potential energy very slowly. So weaker field, in weaker fields, you lose potential very slowly, and so the potential surfaces are farther away. All right, let's take another example, and I want you to take a shot at drawing equipotential surfaces. Let's say we have a infinitely long sheet of charge, big sheet of charge, which has, let's say, negative charge. Then we've seen before, it produces a uniform electric field. Can you think of what the equipotential surfaces here would look like? Can you try drawing a few equipotential surfaces over here? Pause the video and think about this. Use the same approach as we did over here. All right, just like over here, let me go at some distance, say about 2 centimeters from this sheet. It'll have some potential because it's a negative charge. Maybe there is some, I don't know, negative 10 volt potential. Now, if I go 2 centimeters from here, I should get exactly the same potential as here. And the same would be the case over here as well. Ooh, that means I can connect all these lines. And if I do that, now my equipotential surface would look somewhat like this. So this would be my minus 10 volt equipotential surface. I can draw another. If I go a little bit farther away, maybe I will get another, let's say, minus 9 volt equipotential surface. If I go farther away, maybe I'll get another minus 8 volt equipotential surface, and so on and so forth. Over here, I hope you agree that the equipotential surfaces will be equidistant because the field lines are all, the electric field is uniform. And again, just to reiterate, this is not a line, this is a surface. So you have to imagine this in 3 dimensions. I'll help you visualize that. If you could see this in 3 dimensions, so if you look at them in 3D, you can now see that now the equipotential surfaces are plane surfaces. So over here we got spheres, over here we're getting plane surfaces. All right, but here's a question. These were simple cases. But what if we have to draw equipotential surfaces in general? What if I have some random electric field line due to like some complicated network of charges? Something like that, I don't know, just randomly drawing. How would we draw equipotential surfaces then? We may not be able to use the same approach like here, but what we can try to do is see if there is some geometrical relationship between electric field lines and equipotential surfaces. So let's come over here. Can we see any relationship between these field lines and the potential surfaces? If you look very closely, you can see that these equipotential surfaces are perpendicular to the field lines. And that makes sense, right? Because in general, over here the field lines are forming the radius, and the radii are always perpendicular to the spheres or circles. So over here we are seeing that the two are perpendicular to each other. Let's look at over here. Hey, here also we are seeing that the field lines are perpendicular to the equipotential surfaces. Interesting. So can we say that this is true in general? That equipotential surfaces and field lines must always be perpendicular to each other? We can't just say that using 2 examples. We could say that might be a coincidence. So is this true in general? Well, if you and I were in the same room, maybe we would have an interesting dialogue over here, but I don't want to take too much time, and I'll go ahead and tell you that turns out that this is true in general. So let me just write that down. Equipotential surfaces are always perpendicular to electric field lines. Or I can just say perpendicular to field or field lines. Always, regardless of how complex the field lines are. And again, the final question for us in this video is why this is true. And I want you to again pause and ponder upon this. This is a deep question, but I'll give you one clue. Think in terms of contradiction. What would happen if the equipotential surfaces were not perpendicular to the field lines? What gets broken? Think a little bit about that. Like I said, it's a deep question. Don't expect it to get right away, and it's okay if you don't get it right away, but the idea is just to think a little bit about it before we go forward. All right, let's see. There are multiple ways to think about this. The way I like to think about it is, again, bring back my test charge. So here's my test charge. Now imagine we move this charge along the equipotential surface, say from here to here. Now, because it's an equipotential, at every single point the potential is the same, that means the potential energy of this test charge will remain the same as you move it, right? Let me write that down. No change in potential energy, no change in potential energy as you move along the equipotential, by definition, right? Okay, what does that mean? Well, if the potential energy is not changing, it automatically means no work done by the electric field. No work by the electric field. Now think about it for a second. Why should this be true? Because whenever electric field does work, whether positive work or negative work, very automatically potential energy would change. For example, let's bring back gravity, because gravity helps in understanding this. What happens when you drop a ball? Gravitational field does positive work. What happens to the potential energy? It loses it. What happens when you throw a ball up? Gravity does negative work. What happens to the potential energy? It gains it. So notice, whenever gravity does work, this ball would either lose or gain potential energy. Same would be the case over here. If electric field did work, the charge would have gained or lost potential energy. But we are seeing that it is not changing its potential energy. Means that as you go from here to here, electric field must be doing zero work. But how is that possible? Electric field is definitely pushing on the charge, is putting a force on the charge, and the charge is moving. So how can work done be zero? Work done can only be zero if the force and the direction of motion are perpendicular to each other. So, in short, as you move a test charge along the equipotential surface, its potential energy should not change. That can only happen if the electric field does no work. And that can only happen if and only if electric fields are perpendicular to the equipotential surfaces. Now, if you find this a little hard to digest this right away, it's completely fine. It took me also a long time to do that. So keep pondering, keep thinking about it. It'll eventually make sense. So long story short, this basically means if you have been given some random field lines and if you want to draw equipotential surfaces, just start drawing them perpendicular to the field lines. This is how you might do it. And of course, nobody's going to ask you to do that, but we usually use computers to do that, but that's the idea. But equipotential surfaces must always be perpendicular to the field line. All right, let's summarize. And I want you to summarize. And the way to do that is I'm going to ask you 3 questions and see if you can explain it to a friend. What are equipotential surfaces? That's question 1. Second question, why over here these surfaces are going farther and farther apart from each other, but over here the surfaces are equidistant? And third one, why are equipotential surfaces always perpendicular to the field lines? We're given an electric field towards the left, a uniform field which has a magnitude of 100 volts per meter. And we're given 3 points, A, B, and C, and we're asked to figure out what is the potential difference VA minus VB and VB minus VC. So the whole idea behind this problem is we need to find a way to calculate potential differences from electric fields. Now in a previous video, we've seen what that connection is. We saw something, we realized that electric field is a negative potential gradient. Now, if you don't know what that means and you're not familiar with this connection, feel free to pause this video, go back and watch that video, revise the concepts and come back over here. All right, if you're cool with that, let's go ahead with this. Let's start solving the first one. What is the potential difference VA minus VB? How do we do that? Well, one way is we can use the formula, and we'll do that a little bit later, but I want to try and solve this logically. And for that, I ask myself, what does this number even mean? This number says that if you move along the field, then for every meter you go forward along the field, you will lose 100 volts of potential. That's what this number means. And if you're wondering, why do we lose potential as you go along the field? Well, if you keep a positive charge somewhere over here and let go of it, what happens? Well, it'll accelerate along the field, meaning it'll gain kinetic energy along the field, which means it'll lose potential energy along the field. Just like in the case of gravity, as things fall down, they lose potential energy along the field. So I know that if you go for every meter along the field, you lose 100 volts. Or every meter in the opposite direction of the field, you gain 100 volts, which means if there are 2 points which are 1 meter apart, I know that their potential difference will be 100 volts. So that means I just need to figure out how far apart these two are, and then I can calculate. So can you pause the video right now and see if you can, just using this information, figure out what is the potential difference between these 2 points? Give it a try. All right. So the first thing that comes to my mind is I just have to figure out what the distance between these 2 points are. If I know this distance, and let's say I find out that distance to be, and you can use coordinate geometry to figure that out, but let's say you get some number, if, for example, say 10 meter, okay, just an example. Then that means for every meter I gain 100 volts. So for 10 meters, I would gain 10 times 100, so 1000 volts. So would that be the answer? No. That will not be the answer. You can't do it this way. Can you pause the video and think about, okay, another thing, why you can't do it this way? All right. So this number that you gain or lose 100 volt per meter only works when you move in the direction of the electric field or in the opposite direction. Basically, you have to move parallel to the electric field. Only then you can say per meter you gain or lose 100 volts. So you can't move this way. So then how do I go from A to B? The way I like to do it is, one of the ways to do it is, you can go from A to B along the field first, and then you go up this way. I'll tell you why. See, when I go from here to here, I can use this number. I can figure out how far this distance is, and then I can use this number to figure out what the potential, how much potential I'm gaining because I'm going in the opposite direction. And now I'm going from here to here. Notice when I go this way, I'm moving perpendicular to the electric field. And we've already seen before that if you move perpendicular to the electric field, there'll be no change in potential. In fact, these 2 points lie on an equipotential surface. Remember, equipotential surfaces are always perpendicular to electric field. So long story short, from here to here, there is no change in potential. Okay, so that means all I have to figure out is what is the potential at this point. I just need to figure out what is the potential difference between these 2 points. That's the same as the potential difference between these 2 points, because this and all the points lying on this plane would be at the same potential. Does that make sense? So I just need to figure out what this distance is. And I can do that by looking at the x coordinate. So this is -1. This is +4. So what is the difference between these 2 points? That's 4 minus -1, that is 4 plus 1. So that's 5 meters. And you can pause and you can just check that's right. So this is 5 meters. And so now I can use this number. I know for every meter I go forward, I gain 100 volts. So how much would I gain if I go 5 meters forward? I would gain 500 volts. So immediately I know that this point, which is the same as this point, potential-wise, is 500 volts more than this point. So let me write that mathematically. VB is 500 volts more than VA. And therefore, what I need is VA minus VB, so I can just rearrange this and I'll get VA minus VB as negative 500 volt. And we're done. There we go. That's the answer. Okay, now before we go forward to the next one, let's just convince ourselves we get the same answer by using the formula. This will be an excuse for us to get used to the formula. In a previous video, we also derived the formula. We saw that electric field, what is the connection between this and the potential difference? Electric field is the negative potential gradient, which means it's the negative difference in potential between 2 points divided by the distance between the 2 points. And again, this distance is only along the field. Okay, so can you again pause the video and see, by substituting, you end up with the same answer. So give it a shot. All right, so if you rearrange, you get delta V equals minus E times delta R. Now, when you're talking about delta V and delta R, especially delta V, we need to be very careful about which is our initial point and which is our final point, right? Because when we're talking about change, initial and finals are important. Now, over here, we went from here to here, but you don't have to. You could have gone backwards as well. But just to keep things simple, I'll call this as my initial point and this as my final point. This point and this point are the same, by the way, like we just saw. Potential-wise, they're same. All right, so what is delta V now? Delta V is final potential minus the initial potential. So this would be VB minus VA. And that's why it's important. If you had called this as your initial point and this as your final point, you would call this VA minus VB. It'd be opposite. This equals negative. What is the value of electric field? Now we know the magnitude is 100, but what about the direction? It's in the opposite direction of the positive X. And that's important when you're substituting over here. So that means this is negative 100 volt per meter. So negative 100 volt per meter times, what is delta R? Delta R is you're going from here to here. So you're going in the positive direction. So that's plus 5. So 5 meter. So meter cancels and see what we end up with. We get 500 plus 500. So you get 500 volt. So VB minus VA is 500 volt, means VA minus VB is negative 500 volt. So you get the same answer. So you get the same answer. All right, can you think about what would be VB minus VC? Again, can you pause and try? All right, so because point B and C lie on the exact perpendicular, that is the equipotential surface, they are at the same potential, which means the potential difference between them must be 0. And so whether you take VB minus VC or VC minus VB, it should be 0. And again, I could ask, can we use the formula to arrive at this? Yes. This time delta R for them is 0. Because remember, delta R is the distance along the field. The distance along the field is 0. Are you getting that? Along the X direction, they have the same coordinate, and therefore delta R is 0. And then therefore you would get the same answer over here. All right, let's try one more. Okay, in this case, we are given an electric field pointing downwards with a magnitude of 30 volts per meter. We're given a point A whose coordinate is given to us, 3, 10, and there is a point B such that their potential difference is given to us this time. And so our goal is to find what the coordinate is. Again, can you try doing this yourself first? All right. So again, the first thing I want to try and do is see if I can do this logically. Now I know that the first thing I'm looking at is I'm trying to figure out whether B should be above A or B should be below A. It's given to me that VB is more than VA, right? It's a positive number. That means VB has a higher potential than VA. And so I'm just asking myself, if I go down along the field, potential will drop. Oh, so it has to be above. So B has to be somewhere over here. Somewhere over here. Okay, so that's the first thing I figure out. Now I know that for every meter I go up, I will gain 30 volt. But for us, I just have to gain 10 volt. So I ask myself, how many meters should I go up? Well, I like to do it this way. I like to write it down. So I know for 1 meter, if I go up, I know I gain 30 volt. 30 volt. But it's given to me that I just have to gain 10 volts. So how many meters should I go? Well, it's 1/3, and therefore it should be 1/3 over here as well. So 1/3. So I divide this by 3, I get 10, right? So I divide this by 3, and so 1/3 meter, so that is 0.33 meter. So this distance should be, set that down, 0.33. So now comes the question, what is the coordinate of this point? So this point would be, well, the x coordinate would remain the same because x coordinate is not changing, so that's 3. The y coordinate would be now 10 plus 0.33, so it would be 10.33. And there'll be bar. I can put a bar over there. Now, one thing, just like we saw last time, this is not the only point that has 10 volt higher than point A. I can in fact have any point along this line perpendicular because all of these points on this line are equipotential. So point B can be here also. Point B can be this one. So point B can have any value of x coordinate because this is a uniform field. It can have any value of x coordinate, but its y coordinate has to be 10.33, which means the actual answer that we need to give if somebody asks us this question is we could say, hey, it can have any value. It's not that we don't know the value of x coordinate. We're saying it can have any x coordinate it wants. So I'm just going to put x over there. Pick any point you want. And y coordinate has to be 10.33. So this is our answer. And I encourage you to try and check this using the formula yourself. We've defined electric field strength as the amount of force acting on a coulomb of charge, force per coulomb, so newtons per coulomb, right? Now in this video, we will look at a new way of defining electric field strength in terms of potential difference. So let's start by something that we already know. Let's use this definition. So let's take an example. Imagine we have a uniform electric field towards the right, created by some sheet of charge, let's say. And let's say that the strength is 100 newtons per coulomb. Let's start by asking ourselves, what is the meaning of this statement according to this definition? Well, it basically means that if I keep a coulomb of charge in that electric field anywhere, it's uniform, then that coulomb would experience 100 newtons of force, 100 newtons per coulomb. Similarly, what would it mean if I had, let's say, another electric field, say upwards? And let's say this electric field was 500 newtons per coulomb. What would be the meaning of that? Well, this would mean over here, if I now bring that 1 coulomb of charge and keep it over here, then that coulomb would experience 500 newtons of force, 500 newtons per coulomb. Okay, now let's think of this in a different way. And for that, here's my question to you. Imagine I let go of this charge. So I keep my charge over here. I'm holding it right now. Let's say I let go of that charge. What's going to happen? Well, it's experiencing a force towards the right, and so it'll accelerate towards the right. And as it does that, it's going to gain speed. It's going to gain kinetic energy as it goes towards the right, which means it's going to lose potential energy. It's just like a ball falling down. As it gains speed, it loses potential energy, right? So that means as it goes forward, it gains kinetic energy, it loses potential energy. What I want you to try and figure out is how much potential energy this coulomb of charge would have lost if it went forward, or when it goes forward by exactly 1 meter. So can you pause and calculate how much potential energy it would lose by the time it would have traveled exactly 1 meter? So can you pause and try and figure this out? All right, let's see. So let's start by asking ourselves, how do we calculate how much potential energy is lost or gained? Well, that is calculated by the work done. The potential energy lost or gained is the work done by the electric field. And so how much is the work done over here? So the work done over here, let me write that somewhere here. So the work done over here is force into displacement, 100 into 1, that's 100 joules. 100 joules, and that work is done for 1 coulomb of charge. So work done is 100 joules per coulomb. And that means this coulomb will lose 100 joules of potential energy by the time it travels 1 meter. Does that make sense? And all of that 100 joules will get converted into kinetic energy. Another way of saying that is we can say, as I go forward by 1 meter, we will lose 100 joules per coulomb, 100 joules of potential energy per coulomb, meaning 100 volts. Joules per coulomb is also called volts. So let me raise that and let me write this as volts. 100 volts as I go forward 1 meter. So I could say 100 volts per meter. Does that make sense? Think about it. For every meter that I travel forward, I would lose 100 volts of potential in this electric field. Okay. Now, similarly, what can you say about this electric field? How many volts would we lose if you go 1 meter forward? All right. Well, the calculation will be very similar. If I go 1 meter forward, so let's say this is 1 meter, the work done by the electric field would be 500 joules. So 500 joules per coulomb. So 500 volts for every meter you go forward. So in this electric field, we will lose 500 volts, much higher, 500 volts per meter. And this is our new way or new definition of our electric field strength. So our electric field, this number is telling us how much potential gets dropped for every meter you go forward along the field. Okay, and so now let me move this a little down. Okay, let me move this over here. All right, so now we can also say that this electric field equals 100. Instead of calling it newtons per coulomb, I can also say volt, 100 volt per meter. And what does it mean when I say electric field is 100 volt per meter? It's saying that in this field, for every meter you go forward, you lose 100 volts. Similarly, I can now write this as 500 volt per meter. Although there is a volt over here, this is not potential, this is field, volt per meter. And what is this saying? This is saying, oh, this is a much stronger field. For every meter you go forward, you lose 500 volts of potential. So what's our new way of defining electric field strength? We can say it is a measure of how much potential drops per meter as you go forward in the electric field. Okay, and how do we write that mathematically? So let me write that over here. How do we write this mathematically? We could say electric field equals potential drop, which we can write as delta V, per meter, which we can write as per distance. So per delta R or delta X, what do we want to call that? Delta R or delta X. And what's the unit? It's volts per meter. So a new way of looking at electric field. Now, one thing we need to be very careful, this is not complete equation yet. One thing to be careful is, remember, the number is saying how much potential you're losing as you go forward. Remember, it's a drop, okay? And how do we take care of that in the mathematics? Mathematically, when we write it, if I just write delta V, it represents how much potential is gained because it's a positive number. But we are saying it's how much potential is lost. And it's for that reason we put a negative sign over here. So the negative sign is basically saying it's a measure of how much the potential drops. Think of it this way. If your electric field, let's say, is positive, let's say right side is positive. If your electric field was positive, and let's say you also move in the positive direction, delta R is also positive, what would happen to your potential? Would you gain or would you lose? You're losing. That's what we're saying, right? You're losing. And therefore, this needs to be negative. So it's saying that if both these are positive, then delta V has to be negative. And therefore, that's why we have a negative sign. And of course, in a future video, we'll solve some numericals and this will make more sense. But long story short, electric field is a measure of how much potential gets lost for every meter you go forward. Now, before we conclude, there's one last thing I want to mention of how do we write this, how do we say this technically? So whenever you're calculating how much something is changing with respect to distance, or how much something is changing per meter, we give it a name, we call that a gradient. So let me write that. This is called gradient, okay? So if I said something like temperature gradient, it means it's a measure of how much temperature is changing for every meter you go forward. So this is potential gradient because it's a measure of how much potential is changing for every meter you go forward. So our right-hand side is potential gradient. Let me shift this, sorry, there's a little space. So let me try and make this. So this, whatever we're writing, whatever we're calculating is potential gradient. Potential gradient. And therefore we can now say that electric field, this is what you will see in your textbooks, electric field is the negative potential gradient. If I just say potential gradient, it means how much it's increasing. So I have to say how much it's decreasing, how much potential is decreasing. And so we can now say electric field is a negative potential gradient. Sounds very cool to say that, but hopefully now this makes a lot of sense. Basically means how much potential is losing for every meter you go forward. Suppose we are given what the electric potential at every single point in space is. It's given by this function, let's say. And this equation is basically saying you put in the value of any coordinate you want, and then it will tell you what the electric potential at that point is going to be in volts. Our goal is to figure out what the electric field vector is going to be at every point in space. How do we do that? Okay, so to do this, we need to find some connection between electric field vector and the potential function. And we've explored something like this in our previous videos. We've seen that electric field is the negative potential gradient. And what it's basically saying is that imagine you have an electric field and let's say you want to find what the strength of that field is at point A. Then it's saying that all you have to do is take a step forward to say point B, step some distance forward, and you find out how much the potential has dropped. The potential will drop if you move in the direction of the field, right? And that potential drop is delta V. That ratio then, the negative ratio, how much the potential is dropping per meter, that itself will tell you what the strength of the electric field is. And if you're not familiar with this, then we've talked a lot about this in great detail in previous videos. Feel free to go back and check that out. But there are a couple of problems if you try to directly use this over here. One is this will only work for uniform electric fields. I mean, think about it. If you want to step forward and then calculate how much the potential has changed and divide by delta R, then that electric field value should stay same everywhere in between. But in our case, the electric field may be changing. In fact, it might be a non-uniform. That's what I mean. Changing means it may be a non-uniform electric field. Let me draw that. So let's say our electric field is a non-uniform. Then what do we do? Now, as the moment I step forward, immediately electric field might have changed. Then if I do this, I will get an average value of the electric field between point A and point B. I don't want that. I want the electric field at A. How do I do that? Well, we can do something that we've done a lot of times before in physics. We can use calculus. We can say, imagine, instead of taking a big step forward, take an incredibly tiny step forward. Imagine point A and B are incredibly close to each other. So close that practically electric field value is going to be the same. In that case, this distance delta R becomes an infinitesimal, and we often write it as dr. And then you calculate what the how much the potential drops. That will be an infinitesimal drop, and it'll be dV. And then you do a negative dV over dr, and that will give you the electric field at that point. And so now, the only change we have to do is make dV over dr, and now this will work for any field. But there's a second problem. See, I don't even know what direction the electric field is at this point. So how do I know in which direction I should move to calculate this gradient? Because I should always move along the field or in the opposite direction. I don't even know what direction the field is. So how do I know? Should I move to the right, left, up, down? How do I know that? Well, what we can do is we can ignore whatever that we can say, it doesn't matter what direction the electric field is. Let's calculate the X and the Y and the Z component separately. So here's what I mean, okay? So I don't know what the direction of the electric field is. It doesn't matter. What I will now do is I'll take a small step only in the X direction. So let's say our right side is the positive X. So this then would be, R dx. So this is going to be R dx. And as a result, there'll be some change in potential. And now let me calculate that gradient. So if I calculate that gradient, negative gradient, dV divided by dx, what does that give us? I'm now calculating how quickly the potential, or how much the potential has changed per meter along the X direction. So that gives me the electric field strength along the X direction, meaning it tells me the X component of the electric field. So to calculate the X component, I have to differentiate voltage function or potential function with respect to X. But we have to be very careful. See, it's under a condition. The condition is dx is the only variable that's changing. I am not moving, there is no dy, I'm not moving in the y direction, I'm not moving in the z direction, I'm only moving in the x direction. So the condition is dy is 0, there is no change in y, and dz is 0. And why is that? Because I want to calculate the component only in the x direction. So for that, I should make sure that I'm not moving in the y, I'm not moving in the z. Does that make sense? And so that will give me the x component. And similarly, what I can now do is move a small step in the y direction and calculate what that dV is, and then take the gradient. And what will that give me? That will now give me the y component of the electric field. So to calculate y component, I should differentiate voltage, potential function, with respect to y. But again, it's under the condition that now I'm only moving in the y direction. Okay? Because I want to calculate the y component, I have to only move in the y direction. That means now my dx should be 0. Is that making sense? My dx should be 0 and my dz should be 0. And I know this is a little abstract, it might take some time, but I can repeat this. Why am I making sure my dx and dz was 0? What would happen if they were not 0? If my dx was not 0, so let's say dx had some value, then that means I did not move this way. I might have moved at some angle. And if I move at some angle, then I'll get the electric field component along that direction. I don't want that. I only want along the y direction. So I only need to travel this way, meaning dx should be 0, dz should be 0. Is that making sense? And the same thing I can do along the z direction, and that'll give me the z component of the electric field. Oops, dz, making sure dx is 0 and dy is 0. And once I have the three components, I can put together and I can use I cap, j cap, and k cap and write down what my electric field is going to be. So can you now at this point pause the video and maybe take a breather of what we've all done and see if you can now use this, use your calculus, use your differentiation to figure out what the electric field is going to be. So pause and give it a shot. All right, let's do this. So let me make some space in between and start by finding what the Ex is, the X component of the electric field. Now we have to do this, right? And let me show you the notation that we use, a shorthand notation to write this whole thing. The way we write that is we write negative, instead of writing D, we write dou V over dou X. It's just a notation, okay? Don't get scared by that. All it's saying, mathematically all this is saying is that you're only differentiating this function v with respect to x. And if there are any other variables like y and z, and if there are any other variables, they are not changing. That's what it means to say dy is 0, y is not changing, dz is 0, z is not changing. That's how you should differentiate it. Okay, you may be wondering what's the difference, and you will see. Let's do this. You will see now what's the difference between dou and this. Okay, so I'm going to do normal differentiation, nothing different. So normal differentiation, how would you do this? So you have the first term. If you differentiate, it's a uv. So first term x into differentiation of y with respect to x. So I'll just write it as dy over dx. Let's do normal differentiation first, plus the second term into differentiation of the first term, which gives me 1, minus, let's differentiate this now. I get 2 times, 2 comes down, so you get 4y, and you have to use the chain rule, to dy over dx. I haven't done anything funky now. It's regular differentiation. Okay, I've used chain rule wherever required. All right, but now remember, dy and dz are not changing. They are 0, which means this goes to 0. dy is 0. Again, dy is 0, which means this term goes to 0. When you apply this, this is what we mean by dou v over dou x. Okay, so any dy and dz terms, they go to 0. And this kind of differentiation is called partial differentiation or partial derivatives, because you're only differentiating with respect to, we're only making sure changes are happening for x and not y. Okay, so what do you get? So let's see, we get ex equal to, this term goes to 0. This term survives. This is the only term survives. So I get minus y. So this is my x component value. So now let's do the y component. And I encourage you to try that. What's y component going to be? Again, it's going to be negative dou v over dou y. But let's start by doing normal differentiation. And I encourage you to pause and try this. All right. So again, we use uv rule. So first term into differentiation of the second term, differentiation of y with respect to y is 1, plus the second term into differentiation of the first term, differentiation of x with respect to y is dx over dy. Be careful what you're differentiating with. You're differentiating with respect to y now, minus 4y. And now let's use this. dx and dz is 0. So dx is 0, that means this goes to 0. So now this is partial derivatives, whatever you're getting now, okay? So ey is going to be, let's see, this term survives, this term survives, so I get negative x plus 4y. This now is your y component of the electric field. And before we go to z component, let me show you a faster way of doing this instead of just doing the whole thing. A faster way of doing this is we could say, look, in this differentiation, y and z are not changing. So you can treat them as constants. So while calculating the x component, just differentiate this with respect to x and treat y as a constant. Now, if I do this in my head, in the first term, y is a constant. So when I differentiate, this will go to 1 and I'll get y. I'll get y. And this will become 0 because it's a constant. So I'll only get y, and then the negative sign comes. Does that make sense? Similarly, when I'm differentiating with respect to y, treat x and z as constant. There is no z over here, but treat x as constant. So when I differentiate the first term, x is a constant, so I'll get x, and I'll get minus 4y. And then the negative sign basically comes from the outside. And that's how you do this. So what will be the value of Ez now? You have to differentiate only with respect to z, assuming x and y to be a constant. Well, there is no z term. The whole thing is a constant for us. And what's the differentiation of constant? You get 0. And so Ez is 0. And it kind of makes sense. If there is no z term in this, that means when I take a small z side step in the z direction, the voltage doesn't change at all in the z direction. And that means that there is no z component of the electric field. So finally, what is the electric field vector? Let me make some space. Let me move down. All right, so now that I know all the 3 components, I can now say that my electric field vector at any point in space, x, y, z, I will not write that, any point in space is going to be the Ex, which is negative y, I cap. Okay, let me do it step by step, so there'll be no confusion. It's gonna be Ex, I cap, plus Ey, j cap, plus Ez, z component, times k cap. It's Cartesian. Okay, what is Ex? Ex is negative y. So negative y times I cap. Plus, what is the y component of the electric field? It's negative x plus 4y. So minus x plus 4y times j cap. And what is Ez? That's 0. So this is my expression for electric field. And now if you give me any coordinate of x, y, and z, I can just substitute over here and I can find electric field at any point in space. So long story short, if you want to calculate electric field vector from a potential function, you have to separately calculate the 3 components by doing partial derivatives. And what that means is you differentiate only with respect to x, keeping y and z constant, and so on and so forth. And then once you have the 3 components, you put them all together, and then you get the total electric field vector. In this video, we're going to figure out how the equipotential surfaces are going to look like when we have multiple charges, say positive and another positive, or a positive and a negative, or a negative and negative charges. Now, just a quick recap, we've already defined in previous video what equipotential surfaces are. These are 3-dimensional surfaces which have the exact same potential everywhere on top of it. And an example would be for us, a point charge, the equipotential surfaces would be spheres. And one of the amazing properties of these surfaces we've seen is that these surfaces are always perpendicular to the field lines everywhere. And if you're not familiar with this concept or you need a refresher, feel free to go back and check our previous video out. But anyways, now let's bring in another positive charge, and our goal is to figure out logically using this property, we're going to use this property, how the equipotential surfaces is going to change. So if I bring in another charge, so let's say here's another charge over here. You know by now that the presence of this charge is going to change the field lines, right? You may have seen earlier that the field lines are going to sort of change. Maybe these field lines are going to push on each other, and so the field lines are going to move upwards like this over here. These field lines are going to move downwards like this over here, and so on and so forth. And because the field lines change, and because the equipotential surface should always be perpendicular to the field lines, that means our equipotential surfaces are also going to change. So the question is, how would it change? We can't draw an exact thing, but we want to get an intuition for how it may change and what the rough surface would look like. So let me draw the new field line properly over here. Here's what our new field looks like. Somewhat like this. Okay. Now what I want to do to figure out what the new equipotential surface looks like is I want to look at one of these field lines and compare it with what it was before, and then see how the field potential surface should change. This surface should change. So let me get rid of all the field lines and just compare with one of the field lines over here. So if I zoom in, okay. So this was our earlier equipotential surface when the field line was like this, and this was 90 degrees. This was perpendicular. Let me use white. This was perpendicular. But now notice once it has curved, this is no longer perpendicular. So to make this perpendicular, you can kind of imagine this part of the equipotential surface must be somewhat, so let me draw that. Okay, somewhat like this. Somewhat like this. Can you see that? Then it'll be again 90 degrees. And the same thing would happen somewhere downwards. So if I draw one more field line over here, then this equipotential surface, this part of the equipotential surface should also, to make sure it stays 90 degrees, should bend somewhat like this, so that this would stay 90 degrees. And immediately from this, you can kind of see that our new equipotential surface would kind of look somewhat like this. So you can kind of see that it'll be bulged out towards that other positive charge. Can you see that? Okay, now let's see what happens somewhere else. So let me show you one more field line over here. Now let's look at what happens over here. Well, again, notice it's no longer 90 degrees. To maintain that 90 degrees over here, this part of the equipotential surface should be somewhat like this, so that this will be 90 degrees again. And finally, if I draw one more, something very similar at the bottom, you're gonna get something very similar over here. It should be like this to maintain that 90 degrees. And now if I complete this figure, you can see it's going to be a little bit squashed behind. Oof. Oh, so can you see what the picture looks like? It's kind of like going to be an egg-shaped equipotential surface. Now this doesn't look very nice, so let me zoom back out. This doesn't look very nice, but if I get rid of it, this is what it would look like. Somewhat like this. This will be the new equipotential surface. Let me get rid of that. And so if I get rid of our, let me get rid of this. All right, there we go. This is what the new equipotential surface looks like. So it's kind of like bulged. It's kind of like egg-shaped, but it's kind of like bulged towards this one. And the same thing would happen over here. Same thing would happen over here. And so notice what has changed. So let's try and compare what it was before to what it is now. So if I compare earlier, if I only consider individual charges and I don't consider the effects on each other, it would be spheres. But when I do consider the effects on each other, look at what happens. This was before, this is now. So it's kind of like the equipotential surface is trying to merge with each other, kind of like a drop of water. Can you see that? Okay. And in fact, if I draw more equipotential surfaces, they will indeed merge with each other. You can see they're slowly merging. And if I go very, very far away, it's pretty much going to look circular. I have a simulation over here. Let me show you. In this simulation, we can visualize equipotential surfaces. So let me put a positive charge over here, and we get spherical equipotential surfaces. The brightness represents how strong the field is over here. But what's important is spherical, because there's only one charge. Let me put another charge over here, and you can see another spherical. You can imagine they're very far away, and so they're kind of not interacting with each other. So I've kept them very far away. But now let's see what happens when I bring them close to each other. Ooh, can you see that egg shape being formed over here? Look at that, look at that, look at that. That's the egg shape being formed. That's exactly what we saw. And I can now keep them over here and draw a few equipotential lines, and let's see what happens. Let me go ahead and draw that. And there you go. Close to the charges, it's pretty circular because they're extremely dominant. As you go farther away, it's kind of egg-shaped. And then they slowly merge. And if you go very far away, it's going to become more and more circular, because if I go very far away, it feels like these two charges are very close to each other. It feels like a single charge. And so the equipotential surface of a single charge is pretty much spherical. Okay, here's a question for you. What's going to happen if I made one of those charges much stronger than the other? So let me show you. So I'm going to add more charges over here. More charge. This is 2, 3 charges, say 4 charges over here. Okay. What's going to happen if I bring them close to each other? Can you kind of visualize what the new equipotential surface is going to look like? All right, let's see. I can just do that. And again, we can see it's X-shaped and it's merging, but you can kind of imagine this is huge. This is small. And so now if I were to draw the equipotential lines, you can see the difference. Because this is more dominating, it is more circular, and this is becoming very quickly egg-shaped, and then finally they merge together and you get circular. A quick question for you. Instead of 2 positive charges, what if I'd kept 2 negative charges? What do you think is going to happen? Do you think things are going to change, or things are going to remain the same? Can you pause and think about it? Here's the thing. If I've kept 2 negative charges, the field lines are going to look pretty much the same, except that the lines are going to just reverse in its direction, right? And therefore, nothing much would change. So the equipotential surface should look exactly the same. So let me get rid of these charges. So here's one negative charge. Here's another negative charge. You can imagine blue to be that of a negative potential. Again, spherical equipotential surfaces, if I bring them close, notice they merge. And everything you saw for 2 positive charges would be the same for 2 negative charges. So it'll be the same for like charges. And now comes the question. What happens if you have 1 positive, 1 negative? Ooh, that's interesting. So going back to our drawing board, what if one of these charges were negative of equal magnitude? So it's a dipole. How will the equipotential surfaces change? Can you, again, pause the video and think about how the field lines would change, and as a result, how the new equipotential surfaces would look like? It won't be like these. So pause and think about it. All right, okay. So let me get rid of these surfaces. Now the big change is going to be, instead of field lines curving away from each other, they're going to start curving towards each other. Field starts from positive and goes into negative. Let me show you that. Somewhat like this. Which means now on this side, we'll get the equipotential surface to be flatter on this side. And on this side, it'll be sort of bulged. Not exactly bulged, but so it'll be the other way around. So let me show you what I mean. Somewhat like this. Does that make sense? And if I were to draw more equipotential surfaces, you can see as it comes closer and closer to the center of the dipole, it's gonna get flatter and flatter. In fact, right at this point, you can see the field lines are all parallel to each other, and so you'll get a plane sheet over here. So let me show you that. This is what it would look like. And these would never merge with each other ever, because one is producing a positive volt potential, one is producing a negative potential. In fact, I hope you can see right in between the potential is going to be 0. That's why I've drawn a green over there. It's kind of like neutral potential. And again, we can go back to our simulation. So this time we'll bring in one positive charge, one negative charge, and you can kind of see that extension happening on the other side. You can kind of see flattening over here. Now let me draw the equipotential surfaces. There you go. Not exactly like what we drew in our drawing board, but you can kind of see it's becoming flatter over here. And again, what if I made one of the charges stronger and one of the charges weaker? If I made the positive charge a little stronger in magnitude, you can kind of see it's gonna, this positive would start dominating over this negative. And again, let me show you that. So let me add more positive charge over here. And you can kind of see the positive starts dominating. And again, let me draw the equipotential surfaces. And there you go. This is very interesting. Over here, you see a similar trend. It's getting extended on the opposite side like we saw before with the dipole, but you see more effect over here compared to this one because this is dominating. But if you go far away, they eventually merge. Why is that happening? Why is it merging? One's positive and one negative. Oh, that's because if you go far enough, the positive charge dominates and then you start having positive potential. And so that's why eventually if you go far enough, then these two charges merge together. I mean, they will, together they sort of look like a single positive charge, and eventually you start getting spherical positive equipotentials. We have 3 charges kept like this. These are fixed charges, let's say. Now imagine I take this +2 coulomb charge and slowly move it along this path and bring it to this point, such that now it is at a distance of 3 meters. These are all in meters from the charges. The question we want to try and answer in this video is, in moving this charge, how much work did that external agent, that is me, how much work did Mahesh do in moving the charge from here to here? And we also want to calculate how much work did the electric field do when the charge went from here to here. How do we do that? Well, we can always go back to our basics and say, hey, work done is force into displacement. And I can try and do that over here. The problem is that the force keeps continuously changing, right? As I come closer and closer to the charge, the force might start increasing, which means I have to do some integral. And look at that path taken. No, we're not going to do any integrals over here. So to avoid integrals, we introduced the concept of potential energy. But whenever I used to do these calculations, I used to always get confused with the signs. Is it final potential energy minus initial, or is it initial minus final potential energy? And I used to always get confused. So here's what I like to do now. I always like to go back to gravity because that helps me. That's a very simple case. So let's go back to gravity and think a little bit about it. So imagine I have a stone lying on the ground. What happens when I, again, Mahesh, I move it up? What happens? Well, let's say I did 100 joules of work in pushing it up. I do positive work in pushing it up. What happens to the potential energy? Well, if the initial potential energy was 0, when I do work, I add potential energy into this rock, and so the potential energy of the rock increases by 100 joules, right? And therefore, work done by me, Mahesh, work done by the external force, that equals the final potential energy minus the initial potential energy of this system. So let me write that down. So the work that I do, that equals the final potential energy minus the initial potential energy. And what about the work done by the electric field? Well, I go back over here, ask myself, what is the work done by gravity over here? Well, when I'm pushing up, when I'm putting a force on it upwards, gravity is always putting a force on it downwards. So gravity is putting a force in the opposite direction, which means gravity is doing negative work. So the work done by gravity would be -100. Same will be the case over here. The work done by the electric field instead of gravitational field would be the negative of this. So that would be initial potential energy minus the final potential energy. Does that make sense? Don't ever mug this up, because we'll forget that. Always go back to gravity, take a simple case, and that will always help us in coming back over here. So this means all I have to do now is think about what was the initial potential energy of the system, what is the final potential energy of the system, and then we can figure out the work done. So I encourage you to pause this video before we move forward and try it yourself. All right. So let me draw what the initial system looks like. This is what initially it looked like, 10 meters far away from each other. Then once I did that work, the final system looks like this. And so the energy of this would be the final potential energy. And if I subtract that, I'll get the work done by me. One thing you may be curious about is, hey, what about the path taken? Doesn't that matter? No, it doesn't, because electric fields are what we call conservative fields. It doesn't matter what path you take. All that matters is what is the initial state and the final state. The work done is path independent. All right, so let's go ahead and figure out these potential energies. Let's make some space over here. All right, a quick reminder of how we calculate potential energies of a system. We've seen this in the previous video. The way I like to remember is, first think about what is the potential energy of two charges. The potential energy of a system of just two charges would be K, we can call it 1, 2, K, Q1, Q2 divided by R12, where R12 is the distance between these two. And now if you want to calculate potential energy of system of three charges, you take two at a time. It'll be the potential energy of this, plus potential energy of this system, plus potential energy of this system. Same would be the case over here. And then once you substitute, we can subtract and we can get an answer. So again, if you haven't tried before, maybe now would be a great time to pause and try. All right, let's see. Let's start with the final potential energy over here. So that's going to be K. I'm going to keep the K as it is, and I'm going to put a bracket because K will be common everywhere. So first let's take these two charges. So Q1, Q2 is going to be -5 times -5. That's 25. Divide by the distance between them, that's 10. Plus, then let's take these two charges. It's going to be -5 times 2, Q1, Q2, -5 times 2, that's -10. Divide by this distance, that's going to be 3. Plus, let's take these two charges. We'll get the same answer as these two charges. So again, it'll be -10 over 3. And I'll not simplify. Let me just go ahead and write what the initial potential energy was going to be. Sometimes things cancel out. So that's going to be, again, K. I'm going to take these two charges first. We'll get the same answer as what we got over here. So it's 25 by 10. Plus, when I did these two, this time I'll get -10 divided by 10. So -10 divided by 10. And again, I'll get the same over here. -10 divided by 10. I have to now subtract this. So when I subtract, this cancels out. And so finally, what do I get? Okay, you can do this yourself. This is just now subtraction. Let me quickly do it. What I'll do is, this will be -20 by 3, and this is -20 by 10. So I'll take that -20 out. And what I have here is 1 over 3. And what I'll have over here is -1 over 10, because we're subtracting. -1 over 10. And you can check, you can pause and check. So we'll get -20 times K times, what is this? 10 minus 3 is 7, 7 by 30. So this cancels, and that'll end up with -14 over 3. And now I'll substitute for K. You might remember K is 9 times 10 to the power 9. So 3 cancels out. And let me write down over here the final answer. The change in potential energy is going to be -42. So let me write that somewhere over here. Okay. -42 times 10 to the power 9 joules. That's the change. Oops. That's the change in potential energy. Therefore, the work done by me would be just this number, -42 billion joules. 10 power 9 is, I'm just saving space over here. 10 power 9 is billion, so I'll say minus 42 billion joules. And what is the work done by electric field? It's going to be the opposite of that. So I have opposite sign, so it's going to be plus 42 billion joules. And by the way, this is only happening to be true because I'm slowly moving it without any acceleration. Okay, I think I forgot to mention that in the question. I'm slowly moving it without any acceleration. That's important. That's why the total work done would be 0, because there is no acceleration, there is no change in kinetic energy. Let's quickly try one more. We have 3 identical charges kept at the vertices of an equilateral triangle. And let's say an external agent, again, me, let's say, I come in and I move all the 3 charges now. I move all the 3 charges in the given path, and such that they form a new equilateral triangle of having edge length r. And the question now is, in doing so, if I move it very slowly without any acceleration, what is the total work done by the electric field? So can you pause the video and give it a shot? All right. So just like what we saw earlier, the work done by the electric field is the negative of the work done by me. So it's going to be negative of final minus initial. It's going to be initial minus final. So it's going to be initial potential energy minus final potential energy. And the initial system is going to look like, and the initial potential energy will be the potential energy of this system. And the final potential energy will be the potential energy of this system. So I can just go ahead and calculate. So initial potential energy is going to be just like before. I can take 2 charges at a time, K, Q1, Q2 by R. But notice, this is, since they're all equal, it's going to be just 3 times this number. So it's going to be 3 times K, Q1, Q2 by their distance. So it's Q squared by 2R plus Q squared by 2R plus Q squared by 2R. That's going to be 3 times that. Just trying to save some time and space over here. And the final potential energy is going to be very similar. Instead of 2R, it's going to be R. So it's going to be 3K Q squared over R. And now the work done by the electric field is going to be this minus this, initial minus final. You have to be very careful about the signs over here. So everything, there are 3K Q squared by R is common. What remains now inside, let me write that. Let's not do too many things in our head. So 3K Q squared by R is common when I subtract. What remains is a half here minus what remains is a 1 here. So that means I end up with minus half. So I get minus 3K Q squared by 2R. This is the work done by the electric field in changing that configuration. Suppose we have 3 charges kept like this. Our goal in this video is to figure out what the potential energy of this system is going to be. So what do we even mean by potential energy over here? Well, imagine at the beginning, all these charges were very far away from each other. We could say infinitely far away from each other. Then we can ask ourselves, if I were to bring these charges from infinity to these points, how much work would I have to do? How much work I would have to do? That work done gets stored as potential energy. So I basically have to calculate the work done in assembling these charges from infinity to these points. So let's go ahead and do that. So let me make some space and ask this question. How do I calculate that work done in assembling these charges from infinity? Well, we can do it step by step. Here's what I mean. First, we'll imagine an empty universe. There are no charges kept as of now anywhere. And ask myself, and let's say I bring the first charge. You can take any of these charges as your first charge. I'm just going to call Q1 as my first charge. Let me first bring Q1 from infinity and place it over here. And I'm going to ask myself how much work I did over there. There'll be some work done. Let's call that work done as, let me write that over here. Let's call that work done as W1. Then, keeping that charge over there, let's bring in the second charge from infinity to this point. Again, I'll have to do some amount of work. Let's call that work done W2. Let me bring this down a little bit. Okay. And then finally, we'll now have 2 charges kept over there. And then let's think about bringing the third charge in. And then the work done in bringing the third charge will be W3. And this now represents the total work done in assembling the charges. The beauty of electric fields is it doesn't matter how you do that work. It is independent of the path that you choose to do that work. You could have brought this charge first, you could have brought these three charges together, you could have done any ways you want, the total work done would not change. And that's why we choose a path which is the easiest for us, bringing one charge at a time. And so that this total work done would now represents the total potential energy of the system. So now we have to figure out what is the total work done. So let's do that. Let's focus on the first one. So let me dim the other two. All right, so let's start with the first one. How much work would I have to do in moving the charge Q1 from infinity to this point? Remember, there are no other charges in this universe. So can you pause the video right now and think about how much work W1 I would have to do? All right, because there are no other charges in this universe, nobody is attracting or repelling my charge Q1, and as a result, I would have to do zero work. Now at first, this was really hard for me to digest. I used to ask myself, I'm bringing the charge from infinity to this point. I have to make it move, right? So shouldn't there be some work done? Well, think of it this way. Imagine that when it's at infinity, I give it a very slight, very tiny push. And as a result of that push, the charge starts moving. So I did a very tiny positive work in the beginning. And then finally, when the charge comes to this point, I'm gonna give it an push in the opposite direction, exactly the same amount of push in the opposite direction to stop it. And in doing so, I did a little bit of negative work. And so the total work done becomes zero. It's tiny positive, tiny negative. And so in the entire journey, I didn't do, like, net work done was zero. So does that, hopefully that helps. That convinces me that, yeah, indeed, I'll have to do exactly zero amount of work. So the work done in bringing the first charge is zero. All right, now let's think about the work done in bringing the second charge. So let me dim the first one and let's look at this one. What do you think? Do you think I have to do some work over here? Well, yeah, if you imagine that Q1 and Q2 are both, let's say, positive, just to keep things simple, then you can imagine as I bring the Q2, oh, I'm being repelled by Q1. And over here, we'll imagine that Q1 is fixed in place. Somehow we have nailed it somewhere, okay? I know it's in somewhere in space, but somehow we've nailed it. And as I bring Q2, Q1 is going to repel me. So I have to overcome that repulsion. And so clearly I have to do some work. The question now is, how much work do I have to do? So again, can you pause the video and think about this? All right, one way to answer this question is to go back to the definition of work. Work done is equal to force times distance, but then we see that the force keeps changing. As I come closer, force becomes larger, and then I have to do an integral. Oh, no, I'm not gonna do that. We have a faster way of doing this because we've already done all the hard work in the previous videos. So if you remember, we can bring back the concept of potential. We know how to calculate potential at any point. So let's calculate the potential at this point due to this charge. Because this charge is placed, this charge is not yet placed over here. So what is the potential at this point? Let me call that point V2. What is the potential due to a point charge? We know the formula. It is KQ by R. So K into Q, that's this charge, divided by R, this distance, R12. Now you may ask, why am I talking about potential over here? Well, because remember, potential, this number represents how much work I have to do in moving 1 coulomb from infinity to this point. That's the meaning of potential. So if this number is 10, then in bringing 1 coulomb from infinity to this point, I have to do 10 joules of work, which means I know how much work I have to do in bringing 1 coulomb. So now the question is, how much work I have to do in bringing Q2 coulombs of charge? This is for 1 coulomb. So for Q2 coulombs, how much work do I have to do? Well, it's going to be Q2 times this number. Therefore, potentials are so important. So the work done in moving this charge from infinity to this point would be Q2. Let me write that over here. Yeah, Q2 times this number. So let me just copy paste that. So I'm just going to copy this and paste it over here. Q2 times that number. Let me put a bracket over here. So that's that. All right, now let's talk about the work done in moving the third and the final charge. So let me do this And let me bring this now. Again, one way is I can calculate the work done using an integral of force and distance. I don't want to do that. And we can use potential concepts. And again, I want you to pause the video and think about what would be the work done, W3, in moving Q3 from infinity to this point. All right, again, we can use the concept of potentials. If I can calculate what the potential at this point is, that represents the work done in bringing 1 coulomb of charge. Then I just multiply by Q3 and that will be the total work done. So what is the potential at this point? Let me call that potential as V3. What would that potential be? Well, that will be the potential due to these 2 charges at this point. And that'll be the potential due to this charge at this point plus the potential due to this charge at this point. So the potential due to this charge at this point is going to be, again, KQ by R, so KQ1, and when the distance is R13, so you just have to be mindful of which charge you're looking at and what's the distance. And then there'll be potential due to this one will be Q2, KQ2, divided by this distance, that's R23. Okay, and this now, what does this number represent? That's the work done in bringing 1 coulomb from infinity to this point. So what is the work done in bringing Q3 coulombs from infinity to this point? It'll be Q3 times this number. So this is going to be plus Q3 times this number. So again, let me copy this whole thing, copy and paste it over here. And there we go. That's our total work done. And we're done all the hard work. Literally, we did all the hard work. And now we just have to simplify this. So let me make some space. All right, so if we now simplify, we get the total potential energy will be K, Q1, Q2 by R12. I'll add the color a little bit later, okay? Plus, this would be K, Q1, Q3 by R13 plus K Q2 Q3 by R23. And there we have it. That's our expression for the total potential energy. Now, if you look at this expression, it's something very beautiful has come out. If you look at the first term, K Q1 Q2 by R12, that's actually the potential energy of these 2 charges alone. So let me mark that. So this is U12, potential energy of just these 2 charges alone. Similarly, so this one, okay, this one, sorry, this one. Okay, similarly, if you look at these 2, K Q1 Q3 by R13 is the potential energy of these 2 charges alone. Ooh, so this would be U13, this one. So it is this one. And if you look at this one, Q2, Q3, that is the potential energy, this expression is the potential energy of the system of these 2 charges alone. Potential energy of system of these 2 charges alone. So what's interesting is that the total potential energy is the sum of the potential energy of 2 charges taken in pairs. And if we could have more charges, we could just keep on increasing that. So just consider each pair, add their potential energy, and then sum them up. That becomes your total potential energy. Beautiful, isn't it? Of course, this is a very neat way to remember this potential energy formula. But if you ever forget any of this, go back to our basics. And from basics, we will be able to always derive it. Suppose a capacitor is charged to a potential difference V, having a total charge of Q on each plate. The goal of this video is to figure out what is the total potential energy stored in this capacitor. So let's start by asking ourselves, what do we mean by this potential energy and how do we calculate that? Well, before the capacitor was charged, if I look at the uncharged situation, there are no charges, there are no potential difference, we could say the potential energy is 0. So in the process of charging, someone must have separated those charges. Maybe positive charges from here went to here, creating a positive negative charge separation. And doing that requires work, right? Because an electric field would be generated. Let me show you. So imagine we separate positives and negatives like this. So after separating the charges, adding additional positive charges like this, let me write that. Adding additional charges like this requires work because there's repulsion. Just think about it. If I try to add another positive charge over here, it gets repelled by this plate of positive charge. So you need to overcome that repulsion. And therefore, some work must have been done by the external agent. And that external agent can be anyone. That could be a battery, that could be a fairy over here who's doing the charge separation. It doesn't matter. But somebody did that work. And that work done in transferring a total of Q amount of charges from this plate to that work done itself represents the potential energy stored. So we can say that the potential energy stored in the capacitor is the work done by the external agent. And let's say I am the external agent over here, so work done by Mahesh. That is the potential energy. So I have to calculate what is the amount of work I do. So how do we calculate that? Well, if you go back to our basics of work done, we could say it's force times the distance. But by now, you probably know we don't want to use that. Instead, whenever we're talking about work done in electricity, we can use the concept of potential difference. So remember, potential difference itself is a measure of work done. So for example, if the potential difference over here was 10 volt, it basically means that now if I want to transfer an additional 1 coulomb of charge from here to here, I have to do 10 joules of work. Okay, so here's the question. We know that the potential difference between the two plates is V, how much work needs to be done in moving a coulomb from one plate to another. I also know that the total charge transferred from here to here is Q. The question now is, what is the total work I did in transferring that charge? Can you pause the video and think a little bit about it? All right. So what I would do, what my common sense is telling me is that the work done by Mahesh is, well, to move 1 coulomb of charge, I have to do V amount of work. That's the meaning of potential difference. But I moved Q amount of charge, so the total work that I did must be Q times V. And that itself must be the potential energy stored in the capacitor. But that's wrong. Okay, that's wrong. And this is the first part I want you to think a little bit about. Why is this wrong? It's not enough to, just accept that this is wrong, but really to deeply understand why this is wrong. So can you, again, pause the video and think about, why is this wrong? All right, I hope you did some deep thinking. Now to answer this question, let's look at this, charging process step by step. So here's our uncharged capacitor. And let's imagine I am going to do the work, and I'm going to take a very simple approach. I'm going to start taking positive charges from here and start putting it onto this plate. Every time I do that, I create a charge separation. So let me bring in some charges. So you can see positive, but beneath that, I've also put negative charges. So this is neutral. You can see there's a negative charge over here. So I'm just showing some positives and negative charges. Right now, the plate is neutral. And what we'll do is we'll slowly, in each step, move the charges and look at how much work am I doing. So let's move the first charge. When I'm moving the first charge from here to here, I ask myself, hey, in doing so, how much work do I do? Well, this is a very tiny amount of charge. I don't know, maybe you can say delta Q. It's not the entire charge Q, maybe a small delta Q amount of charge. What is the potential difference right now before I moved it? The potential difference right now is 0 because there is no charge. And therefore, to move that first charge, it's almost free. That kind of makes sense because I don't see any repulsion coming from this plate. I know as I move it, I still get some attraction and I still get some, I do have to do some work. But if we neglect that, I can say pretty much the work done in the first, when I'm moving the first charge is almost 0. So let me write that. I'm going to write how much work I'm doing over here. So the work that Mahesh is doing, in the first step, the work done, I'm just going to call almost 0. So we're going to do it step by step. Okay, now let's move the second charge. Now when I move the second charge, do I have to do some work? Yes, I do, because now I feel repulsion from this charge. In fact, as a result of this charge separation, there is a tiny potential difference generated. It's not as big as this, it's really, really small, but a tiny potential difference is generated, so I have to do some work against that potential. And so now, I have to do some work. So the work done in the second step is going to be some tiny potential difference. I'm going to use the same formula. Work done equals potential difference times charge transferred. So some tiny potential difference multiplied by the charge transferred. How much am I transferring the charge? Some tiny amount. I'm just going to call that dq. Usually small charges you call dq. And let's continue this. So now I move the third charge. And as I'm doing that, notice the potential difference has now increased. Ooh, now it's gonna become even harder for me. So in every step, as I transfer more and more charges, it becomes harder and harder. Next step, it becomes even harder because the potential difference has even increased more. I feel more repulsion. It becomes harder and harder and harder. So what I see is that in every step, the potential difference starts increasing. So in the next step, the potential difference is a little higher. That's why I'm writing a little bigger V to show that the potential difference is now a little higher times dq. In the next step, the potential difference is even more higher. Next step, even more, even more. And so in every step, this V keeps on increasing. Finally. Now imagine I'm transferring the last charge. Imagine I'm almost done and I'm transferring the last charge. Okay, all 1 billion charges have been transferred. Now what's the potential difference? Well, when I'm transferring the last charge, my capacitor is almost completely charged. Now the potential difference is V. And so my last charge that I'm transferring, I have to muscle through a lot of repulsion and I'm doing the maximum amount of work. The work that I do now goes through the potential difference, capital V. So now and only now, when I'm transferring the last charge, that's when I transfer the charge to the big potential difference. And so clearly, if I add up all these charges, all the dqs, I should get the total charge transfer Q. I should get that. But can you now see why the total work done is not just Q into V? Can you, again, at this point, can you pause the video and come up with an explanation by looking at this summation? It's mathematical now. Why is it not Q times V? All right, hopefully you tried. The main reason is because not all the charges went through the potential difference, capital V. Only that last dq went through it. And that's why, because not the rest of the charges went through smaller potential difference, the work done for the rest of the charges is smaller, the total work done should be less than QV. Does that make sense? Okay, so now, how do we calculate this summation? Well, here's a clue. This dq, if you ask me, we know that dq is a small amount of charge, right? So it's a small fraction of Q. How small is a fraction of Q? Well, it's an infinitesimally small part. Meaning we have taken Q and divided into almost an infinite amount of parts, and each tiny infinitesimal is what we call as dq. That means this is an infinite summation, and whenever you're doing something like this, we call that an integral. So we have to set up this integral. So how do we set up the integral? So whenever you're integrating, you will always have a starting point and an ending point. In our case, we have a starting charge of 0 and we have an ending charge of capital Q. So whenever you're integrating, you start with somewhere in middle. So let's consider this situation where right now, let's say the charge on this plate, negative charge minus Q, and the charge on this plate is plus Q. It's not as much as capital Q, it's less than that, some value, some random value. And as a result of this, there is some potential difference which is less than this number. So I'm gonna call that as small v. And now let's assume that we're gonna transfer an additional charge, and that's how we usually do an integral. So let's now calculate how much work, tiny amount of work that we need to do in transferring an additional charge from here. So an additional charge of dq from here to here. How much work do I need to do? Well, that work done, that small amount of work that I have to do would equal, same formula, it's gonna be the potential difference V times the charge dq. And I could ask now, hey, what is that potential difference? Do I know what that potential difference is? Well, think about it. If I know the capacitance, and let's say the capacitance of this capacitor is C, then we know the capacitance formula. Capacitance is how charge divided by voltage. So at any point, voltage, so let me write that down. Capacitance is charge by voltage. So at any point, voltage should equals charge divided by capacitance. So I know that my voltage at this point should be the charge right now divided by capacitance. So this is the tiny amount of work I did in transferring a small amount of charge dq. Now to calculate the total work done, I integrate this expression. So the total work done by Mahesh, that's going to be an integral of this expression, Q by C of dq. So basically I'm writing the same thing, but in a proper integral notation. And from where to where? What is the initial initial charge I'm taking? The initial charge is 0. I'm starting from 0, right? From Q equals 0. And to what is the final charge I want on my plate? The final charge I want on my plate is capital Q. So from Q to capital Q. And now if we integrate this, we'll get the work done, and that'll be our potential energy. So again, good time, and this is the last time I want you to pause the video and see if you can calculate this integral. All right. So since we're integrating Q with respect to dq, you can recall the integral formula. If you're integrating x power n with respect to x, it's going to be x power n plus 1 divided by n plus 1. So let me keep that denominator c. So over here you'll get q power 1, so it's going to be q power 1 plus 1, that's q squared divided by 1 plus 1 by 2. And whenever we're integrating, we're going to put our limits from 0 to q. So let me make some space. And so we put down our upper limit, so that's q squared over 2c minus the lower limit, that is 0. And therefore, this is our work done. And hence, and now let me write that somewhere over here, the total energy stored must be, in a capacitor, must be q squared divided by 2c. And if I substitute Q is equal to C into V, I can say total charge should be equal to total capacitance into voltage. If I substitute that, I can also write this equals, let's see, I'll end up with half. If I put CV, C square V square, square cancels, you'll get C V squared. And if I substitute for C over here, C is equal to Q over V, then I'll get, and you can do that yourself, you'll get it as half QV. Half Q times V, and you can check that. All I'm doing is substituting these values over here and changing the variables. And what's interesting is that whatever we had predicted wrongly, the actual answer is half of that. And although that's not very logical, you can't logically, I mean, it's hard for me to logically explain why it's half, not 1/3 or 1/4, because there's an integral coming, but at least it makes sense that it's less than what we predicted because of what we explained earlier. Not all the charges are moving through that entire potential difference, capital V. So this is how we calculate the energy stored in a capacitor. This picture shows a couple of girls standing inside a metallic cage, and somebody is trying to electrocute them using lightning, and nothing seems to be happening to them. She seems happy. Why? Now, if you're thinking, hey, maybe the electricity is not much over here, maybe it's a very tiny spark, well, the same effect can be reproduced using millions of volts, lightning which is produced due to millions of volts of potential difference using what we call Tesla coils. And you can see the same effect. People inside a cage, lightning is striking that cage, but nothing happens to them. Why? Well, metallic cages are basically conductors. So let's explore how conductors deal with electric fields, and maybe we'll be able to answer this question by the end of the video. Say we have a positive charge kept somewhere in space, and close to it, we're gonna keep a spherical conductor. Imagine a metallic sphere with a hole inside of it, with a cavity inside. And let's say it's neutral. The question now is, if we are in electrostatic conditions, meaning there are no moving charges, how would the electric field change due to the presence of this conductor? We can begin by asking, why should the electric field even change because we have kept a conductor now? Well, here's the thing. Conductors have free electrons inside of them. And so if you consider a free electron somewhere over here, because there's an electric field, it's going to put a force on this electron. Because it's negative, the force would be in the opposite direction of the field direction. And as a result, this electron would start moving. But we said, hey, we want to be in electrostatic condition, which means this cannot be in electrostatic conditions. In this condition, electrons will start moving. So again, the question is, if no electrons are moving, how would the field look like? Can you pause the video at this point and try to give it a shot? Try to think about how the new field would look like. All right. So if we don't want any electrons to move, the condition is simple. There shouldn't be any electric field inside the conductor. So in electrostatic situation, the field inside the conductor must be 0. So we can go ahead and we can delete the field inside. So let me just rub this field. So the field inside must be 0. Then and only then, electrons inside the conductor will no longer experience a force. And this is nothing special. There's nothing special about a spherical conductor. This has to be true for any conductor, which means we can now go ahead and write a general conclusion. In electrostatic conditions, electric field inside any conductor must be 0. But you could ask, well, what exactly is happening? What's happening to that electric field? And well, here's how I like to think about it. We've already seen these electrons are gonna, when there was a field over here, the electrons start migrating towards the positive charge. And as a result, they end up coming somewhere over here. They can't move outside the conductor because it's an insulator. Imagine it's vacuum. So they will all get migrated somewhere over here. So all our negative charge will get accumulated over here. And because this is a neutral conductor, if the negative charge gets accumulated over here, it must have left a positive charge somewhere. And wherever there's a positive charge, more electrons would just keep accumulating. Eventually, there will be a positive charge somewhere on the outer surface of this conductor, somewhere like this, so that the total charge on the conductor must still be 0. Charge conservation. We cannot create or destroy charges. And because of this positive and negative separation, they are now going to start producing their own field. They're going to start producing a field inside. Let me use a different color for that. Let's say I'm going to use blue to represent the field that they have generated. So they might generate a positive and negative field that would look like this. And guess what? This field, the internal field, exactly matches and cancels with the external field. And because of that, the total field goes to 0. Now you may ask, how do you know that it exactly matches? Well, it has to. Because if it didn't exactly match and it didn't go to 0, electrons would still be moving. So think of it this way. The electrons will keep moving until the electric field generated inside matches and cancels out with the electric field from the outside, making sure that the net electric field inside the conductor has to be 0. Beautiful, right? So is this how our electric field is going to look like? No, not really. We're still not done yet, and things are going to get more interesting now. Now think about this. Because electric field everywhere is 0, this means that our entire conductor must be an equipotential surface, meaning that every single point on the surface or inside the surface, inside the conductor, should have the exact same potential. Now, again, I want you to pause the video and think a little bit about why should this be the case? Why, if we say electric field is 0, it should be an equipotential surface? Can you try and make that link yourself? All right, here's how I like to think about it. Consider any 2 points on this conductor. Maybe say one point inside over here, maybe another point inside the cavity somewhere over here. Now imagine you have to take a charge from point A to point B. In doing so, how much work would you do? Well, think about it. There is no electric field inside. If there's no electric field inside, you don't have to do any work against the electric field, which means you do 0 work. And that should be true for any 2 points. So let me write that down. This means the work done in moving any charge between any 2 random points A and B should be 0. In other words, potential at A must be exactly equal to potential at B. And A and B can be any 2 points on the surface, inside the cavity, any 2 points, because there are no electric fields. And what does that mean? That means the potential everywhere must be the same, meaning our entire conductor is an equipotential surface. So another interesting thing we see is that in electrostatic conditions, conductors, the entire conductor must be an equipotential. Again, nothing special about spherical conductors over here. All conductors should obey this rule. But you may ask, okay, how does that affect our electric field? Well, remember one property of an equipotential surface? These surfaces must always be perpendicular to electric field. And if you're wondering why should this be the case, we've spoken about this in great detail in a previous video on equipotential surfaces. So feel free to go back and check that out. But here's the thing. Over here, if you look now, this means that all these field lines which are touching our conductor must be perpendicular to the surface, and they're not. Over here also notice they're not perpendicular. This angle, these are not perpendicular. So somehow the field lines must change, must bend to ensure this is true everywhere on the surface. So again, can you pause the video now for one last time and think about, try to draw a sketch of what this would look like. All right, here we go. So the field lines must bend in such a way as to they are perpendicular at every point they are meeting the conductor. And so if you look at this, this means that this conductor is sort of like sucking the electric field. And that's why even these field lines are gonna sort of like bend towards our conductor, because they're gonna sort of like getting sucked. Now look at how complicated this situation has quickly gotten. But we now understand that. We understand why this has to be true, because it's an equipotential surface, because of some basic rules that we had learned earlier. Now let's see if we can answer our original question. Imagine this field was incredibly strong and there was air over here. In such cases, you can get lightning. And we'll talk more about how that happens and all that fun stuff in the future videos. But let's say there is this lightning strike happens. Now where will that lightning go? Can it enter inside the conductor? Well, remember, lightning is basically charges moving in an electric field. Now, if there is no electric field inside a conductor, the charges will not move inside the conductor. So what will happen is that these electrons or these charges will find a way to go through the surface and eventually somehow go into the ground. This means if there was somebody standing inside the conductor, and let's say she was touching the inner surface, she will not be electrocuted by that lightning. Now here it doesn't look so dramatic because it's a thick conductor, but the same thing would work even if it was an incredibly thin conductor. And that's exactly what's happening over here. This is a closed conductor. Electric fields cannot penetrate inside this conductor, because of which when she's touching the inner surface, the lightning cannot enter the surface, and that's why she's not getting electrocuted. This effect is called electrostatic shielding, because as we can see that the inner surface is shielded from the outer electrostatics. And this was first discovered by Michael Faraday. And so a closed metallic conductor is often also called a Faraday cage. So we would say that these girls are standing inside a Faraday cage, which is shielding them from the outside electrostatics, and that's why they're not getting electrocuted. This is also the reason why airplanes can get struck by lightning and nothing will happen to the inside, because the entire airplane is a metallic body. It acts like a Faraday cage, and therefore lightning will not penetrate. And in most cases, even when the lightning strikes an airplane, it doesn't do any damage. Let's explore how charges get distributed when we add them to a conductor. So let's start by looking at a spherical, imagine this is a metallic sphere which has a hole inside of it. So there's a cavity inside, and let's say right now this is neutral. Now imagine I'm gonna pull some electrons from inside the metal. Don't ask me how I do that. Imagine I just pull them off. And as a result, because I'm pulling electrons out, it's gonna leave behind some positive charges. So now this conductor is positively charged. And here's the thing. These positive charges are all going to start repelling each other. And because conductors have free electrons, because charges can move freely inside a conductor, these charges would want to go as far away from each other as possible. You can imagine the way that happens is electrons from somewhere over here get attracted by the positive charge and they start moving. As a result, they leave positive charge behind somewhere over here, and more electrons can swoop in, and so on and so forth. Which means that these charges are going to start moving. These positive charges will keep moving, but eventually they will stop, right? And so the question now is, when these positive charges have stopped moving, in other words, we have reached electrostatic condition, what would the new arrangement of these charges look like? And I have a few options for you to pick from. One of the option is these charges distribute themselves throughout the entire conductor. You'll find them in the inner surface. You'll find them throughout the bulk of the conductor. You'll also find them on the outer surface. Charges will not be inside the cavity because there's nothing inside the cavity. You can imagine it's vacuum. There's nothing over here, so you can't have charges. So this is one option, one of the ways in which charges could rearrange themselves. But another option could be maybe all the charges, for some reason, they only redistribute themselves on the outer surface of the conductor. That's another option. Or maybe the charges distribute themselves on the outer surface and the inner surface of the conductor. And the goal is to figure out which one of this is going to be and why. The why part is also super important. And before you start thinking, let me give you a little bit of a direction as to how could we even start thinking about it. Well, we can start by using something that we already know about conductors in electrostatics. inside the conductor, electric field must always be 0 at electrostatic condition. Why should this be the case? Because if electric field was not 0 everywhere inside the conductor, then electrons would move due to that electric field and we would not be in electrostatic condition. And we've talked more about this in great detail in our previous videos on electrostatic shielding and Faraday cages. So if you need more refresher, feel free to go back and check that out. So what we could do is figure out in which of these cases electric field through the conductor stays 0. So why don't you pause the video now and give it a shot. All right. Now, even at this point, if you had asked me, I would still say it's a little hard because I would ask myself, how would I know if there's an electric field that exists everywhere? For example, there are positive charges, but because there are so many, maybe the electric fields just cancel out everywhere. How do I know if electric fields exist or not? Well, to calculate electric field from charges, one of the things that we can use is Coulomb's law. But it gets so messy because Coulomb's law only works for one charge, and there are so many charges over here. But guess what? There's another law we can use to think about electric fields. Remember? Gauss's law. Our old friend Gauss can come back and help us now. Gauss's law states that if you consider any closed surface, the flux through it, the electric flux through it, must equal the total charge inside that surface divided by epsilon naught. So here's the thing. I can just choose a closed surface, imaginary surface, and check whether there's any charge enclosed. If there is an enclosed charge, I know that there should be some flux, and therefore I know there should be some electric field. Okay? So I can use this law and figure out whether electric field exists in these three options or not. So again, if you couldn't do it earlier, maybe now would be a good time to see if you can try this on your own. All right, let's do this. So let's look at the first one. Because I want to check whether there's an electric field somewhere inside the conductor, in the conducting part, because that's where the electric field has to be 0, let me choose a Gaussian surface that goes through this part of the conductor. And I'm just going to choose a nice spherical Gaussian surface. So here's my nice sphere. And now I ask myself, is there charge enclosed by this Gaussian surface? Yes. There is a charge. Q inside is positive. You can see all the charges are enclosing that, which means I do have a positive flux. And therefore, there must be some electric field. There must be electric field everywhere over here. And therefore, this is a wrong option. Because from Gauss' law, this tells me that the electric field inside is not 0. Because there is some flux. If electric field everywhere was 0, I wouldn't have gotten any flux. And therefore, I know now there is electric field is present, and therefore this is a wrong option. That leaves us with two options. Again, can you pause right now and see which of the two options would be right? All right, let's look at this one. This seems reasonable. There are no charges over here, so maybe there wouldn't be any electric field. How do I check? Well, again, choose a Gaussian surface. I'm going to choose a Gaussian surface, again, just like before. And now I ask myself, is there charge enclosed by this Gaussian surface? And the answer is yes. The charges on the inner surface are enclosed by this Gaussian surface, which means, again, there is a non-zero flux. There's a positive flux, meaning there must be a non-zero electric field. Ooh, which means even this is wrong. I mean, this is so amazing. Without Gauss's law, I wouldn't be able to guess this, but Gauss's law makes it so easy for me. I know that this is also wrong. So charges can neither be present in the bulk of the conductor, nor can they be present in the inner surface of the conductor, which leaves us with only one option. The charges can only reside on the outer surface of a conductor. Beautiful, isn't it? And we can just go ahead and check it. Now let me draw a Gaussian surface. If I now draw a Gaussian surface, is there any charge enclosed? No, there isn't. And so charge enclosed is 0, and therefore flux is also 0. And because it's symmetrical, we can now say electric field everywhere is also 0. So this is the only one that satisfies that condition, and therefore this is how charges will redistribute themselves. So this means whenever we're dealing with conductors, and this, by the way, only works for conductors. If this was an insulating material, charges would just stay there. They would not redistribute because they're not free to move. But in conductors, charges will always redistribute themselves on the outer surface, because this is the only way electric field inside the conductor can stay zero. One last question I have is, how would these charges distribute themselves on the outer surface? Would they be uniformly distributed? Or maybe because they were initially charged over here, maybe there is more charges over here and there could be less charges over here. What do you think? Well, because this is a sphere, it has spherical symmetry, therefore the charges must also be symmetrically distributed. And so because of its spherical shape, they have to be uniformly distributed on the outer surface. But what if it was not a sphere? What if it had some bumps over here? What if it had some irregular shape? Then it won't be uniformly distributed. And then if you ask me how would it get distributed, again, we'll have to dig into it a little deeper. We'll have to do some more analysis, something we'll do in future videos. Let's talk about field energy, how much energy is stored in an electric field, and derive an expression for that. And I'll also tell you why this concept truly blows my mind away. Now, because we want to keep the math simple, we'll derive this expression using a familiar setup. So we'll take a charged capacitor. Imagine we have some capacitor which is charged to some voltage. Let's start by asking ourselves, what is the energy that is stored in this capacitor? We've already derived that expression in previous video. So the energy stored in that capacitor, let me use green for energy. U is, there are multiple equations. One of the equation happens to be, and the one that I want to use over here is half CV squared. Now, because I want to talk about energy stored in electric field, what we'll do with this equation is we'll try to somehow bring electric field into this equation and get rid of C and get rid of V. So I want you to think a little bit about how can we do that? How can we bring electric field in this equation? Well, I'm looking at potential difference over here. We've seen the connection between electric field and potential difference again in previous videos. We've seen that electric field can be thought of as the negative potential gradient. What does that mean? It basically means you can think of electric field as how much potential difference exists per meter, right? That's a way to think about electric field. And over here, D is the distance over which that electric field exists. That basically is the distance between the plates of the capacitor, because this is where the electric field will exist. So that's how I can bring electric field into the picture by substituting for V. So V happens to be, from this equation, minus E times D. Okay, that's great. I also want to get rid of that capacitance. I don't want that. Okay, how can I do that? How can I get rid of the capacitance? Can I substitute something for this? There's a parallel plate capacitor over here, so probably we can substitute the expression for parallel plate capacitor, which you probably studied earlier, and we can see what we get. So why don't you pause the video, substitute that expression, and see what we get. All right. So the equation for the capacitance or parallel plate capacitance is, we've seen before, it's epsilon naught into A divided by D, where A is the area of the plates and D is the distance between the plates. So if I substitute that over here, let's see what I get. What I'll end up with is half C, which is epsilon naught into A divided by D, multiplied by V, which is the potential difference, which I can write as negative E times D. When I square that, the negative sign goes. That's great. So I'll end up with E square D square because I'm squaring it. All right. So we can simplify. The D goes away. And so what I get now is U, that is the energy stored in the capacitor, equals half epsilon naught. Let me write the E square first. I got what I wanted. Multiplied by area times the distance. What is that? Well, in general, that may not make any sense, but over here, this is the area of the plate multiplied by the distance between the plates. When you multiply that, you're actually calculating the volume of the space in between the two plates, right? So that's the volume. So I'm just gonna write it as the volume. And because I only want electric field on this side, I'm gonna divide by volume on both sides. And when I do that, what I'll end up with is, let me just cancel that volume over here, bring that volume over here. This is the expression that I end up with. Now, why is this mind blowing? Because all I did is took an equation that we were familiar with, did some substitution, and yeah, I got another equation. But let's see what this equation is trying to tell us. So on the left hand side, I have energy stored in the capacitor divided by the volume of the capacitor. What is this? What is this? Well, when you take mass and divide by volume, you get density. It's a measure of how crowded mass is or how compact mass is. Charge divided by volume is charge density, measure of how compact or how crowded charge is. So what do you think is energy divided by volume? Well, it has to be energy density. So let's write that. This is energy density. It's a measure of how compact or how much energy is crowded in this space. So why is this concept so special? Well, if I asked you, hey, where is this energy stored? What would your answer be? Well, you would say, hey, this is basically electrostatic potential energy. It is the energy stored in the charges, the configuration of charges, just like how gravitational potential energy is stored in the masses, configuration of masses, right? Yes, now a different way to look at it is we are saying, hey, this is the energy stored in space, in vacuum. And how can vacuum have energy? Well, because there is electric field. So what this is saying is, in separating the charges, we have created an electric field. And that energy is not stored in charges, but it's stored in electric field. Field itself can have energy. And this is so incredible because this means vacuum. There's no stuff over here. Even though vacuum has nothing, due to fields, it can store energy. Have you ever imagined vacuum having energy? That's a pretty radical concept. Now, don't think that this is a new kind of energy, not at all. It's just that we earlier thought of this energy as energy stored in charges. Now we're looking at that same electrostatic potential energy and looking at it in a different perspective. Looking at this new radical perspective, we're saying it's energy stored in electric fields, energy stored in space. And this can, motivate all sorts of deep philosophical questions like, hey, is energy real? Is the field real? And we can debate about that for hours together. And that's why this concept is so incredible and deep. But besides all these thought-provoking motivations, there's another practical reasons why this equation is so awesome. You see, although we derived this expression for a very special case where we had a parallel plate capacitors and we have this nice and uniform electric field, turns out that this expression holds true in general. It doesn't matter whether you have capacitors or not. In general, if you have a field, electric field, uniform or not, the energy that the electric field carries in space, the energy density in space, will always be this number, half epsilon naught E square. And the units, of course, would be joules per meter cube. So this is a general expression for how much electric field carries energy density. And why that's important is because you might know that light is a form of energy, right? However, about 300 years back, if I asked anyone in the world, hey, how do you calculate the energy that the light carries? Nobody would have a clue because nobody knew what was light made of. Of course, you would have some clue that brighter light has more energy, but you wouldn't know how to mathematically calculate it. However, you might now know that today we know that light is an electromagnetic wave, which basically says that light is made of electric and magnetic fields. So this means if I have to calculate how much energy light carries, all I have to do is figure out how much energy is present in the electric fields and the magnetic field. And since this is a general expression, I can use the same expression to calculate how much energy is present at least for the electric field part of the light, and a similar expression can be derived, and so I can also use that to calculate how much energy the magnetic field part contains, and that total energy will now represent the energy of light. And so what really blows my mind away is that never in my wildest dreams did I think that by calculating how much energy a capacitor has, I would be equipped to, at least in part, calculate how much energy light carries. That's insane if you ask me. Let's talk about field energy, how much energy is stored in an electric field, and derive an expression for that. And I'll also tell you why this concept truly blows my mind away. Now, because we want to keep the math simple, we'll derive this expression using a familiar setup. So we'll take a charged capacitor. Imagine we have some capacitor which is charged to some voltage. Let's start by asking ourselves, what is the energy that is stored in this capacitor? We've already derived that expression in previous video. So the energy stored in that capacitor, let me use green for energy. U is, there are multiple equations. One of the equation happens to be, and the one that I want to use over here is half CV squared. Now, because I want to talk about energy stored in electric field, what we'll do with this equation is we'll try to somehow bring electric field into this equation and get rid of C and get rid of V. So I want you to think a little bit about how can we do that? How can we bring electric field in this equation? Well, I'm looking at potential difference over here. We have seen the connection between electric field and potential difference again in previous videos. We've seen that electric field can be thought of as the negative potential gradient. What does that mean? It basically means you can think of electric field as how much potential difference exists per meter, right? That's a way to think about electric field. And over here, D is the distance over which that electric field exists. That basically is the distance between the plates of the capacitor, because this is where the electric field will exist. So that's how I can bring electric field into the picture by substituting for V. So V happens to be, from this equation, minus E times D. Okay, that's great. I also want to get rid of that capacitance. I don't want that. Okay, how can I do that? How can I get rid of the capacitance? Can I substitute something for this? There's a parallel plate capacitor over here, so probably we can substitute the expression for parallel plate capacitor, which you probably studied earlier, and we can see what we get. So why don't you pause the video, substitute that expression, and see what we get. All right. So the equation for the capacitance or parallel plate capacitance is, we've seen before, it's epsilon naught into A divided by D, where A is the area of the plates and D is the distance between the plates. So if I substitute that over here, let's see what I get. What I'll end up with is half C, which is epsilon naught into A divided by D, multiplied by V, which is the potential difference, which I can write as negative E times D. When I square that, the negative sign goes. That's great. So I'll end up with E square D square because I'm squaring it. All right. So we can simplify. The D goes away. And so what I get now is U, that is the energy stored in the capacitor, equals half epsilon naught. Let me write the E square first. I got what I wanted. Multiplied by area times the distance. What is that? Well, in general, that may not make any sense, but over here, this is the area of the plate multiplied by the distance between the plates. When you multiply that, you're actually calculating the volume of the space in between the two plates, right? So that's the volume. So I'm just gonna write it as the volume. And because I only want electric field on this side, I'm gonna divide by volume on both sides. And when I do that, what I'll end up with is, let me just cancel that volume over here, bring that volume over here. This is the expression that I end up with. Now, why is this mind-blowing? Because all I did is took an equation that we were familiar with, did some substitution, and yeah, I got another equation. But let's see what this equation is trying to tell us. So on the left-hand side, I have energy stored in the capacitor divided by the volume of the capacitor. What is this? What is this? Well, when you take mass and divide by volume, you get density. It's a measure of how crowded mass is or how compact mass is. Charge divided by volume is charge density, measure of how compact or how crowded charge is. So what do you think is energy divided by volume? Well, it has to be energy density. So let's write that. This is energy density. It's a measure of how compact or how much energy is crowded in this space. So why is this concept so special? Well, if I asked you, hey, where is this energy stored? What would your answer be? Well, you would say, hey, this is basically electrostatic potential energy. It is the energy stored in the charges, the configuration of charges, just like how gravitational potential energy is stored in the masses, configuration of masses, right? Yes, now a different way to look at it is we are saying, hey, this is the energy stored in space, in vacuum. And how can vacuum have energy? Well, because there is electric field. So what this is saying is, in separating the charges, we have created an electric field. And that energy is not stored in charges, but it's stored in electric field. Field itself can have energy. And this is so incredible because this means vacuum. There's no stuff over here. Even though vacuum has nothing, due to fields, it can store energy. Have you ever imagined vacuum having energy? That's a pretty radical concept. Now, don't think that this is a new kind of energy, not at all. It's just that we earlier thought of this energy as energy stored in charges. Now we're looking at that same electrostatic potential energy and looking at it in a different perspective. Looking at this new radical perspective, we're saying it's energy stored in electric fields, energy stored in space. And this can, motivate all sorts of deep philosophical questions like, hey, is energy real? Is the field real? And we can debate about that for hours together. And that's why this concept is so incredible and deep. But besides all these thought-provoking motivations, there's another practical reasons why this equation is so awesome. You see, although we derived this expression for a very special case where we had a parallel plate capacitors and we have this nice and uniform electric field, turns out that this expression holds true in general. It doesn't matter whether you have capacitors or not. In general, if you have a field, electric field, uniform or not, the energy that the electric field carries in space, the energy density in space, will always be this number, half epsilon naught E square. And the units, of course, would be joules per meter cube. So this is a general expression for how much electric field carries energy density. And why that's important is because you might know that light is a form of energy, right? However, about 300 years back, if I asked anyone in the world, hey, how do you calculate the energy that the light carries? Nobody would have a clue because nobody knew what was light made of. Of course, you would have some clue that brighter light has more energy, but you wouldn't know how to mathematically calculate it. However, you might now know that today we know that light is an electromagnetic wave, which basically says that light is made of electric and magnetic fields. So this means if I have to calculate how much energy light carries, all I have to do is figure out how much energy is present in the electric fields and the magnetic field. And since this is a general expression, I can use this same expression to calculate how much energy is present at least for the electric field part of the light, and a similar expression can be derived, and so I can also use that to calculate how much energy the magnetic field part contains, and that total energy will now represent the energy of light. And so what really blows my mind away is that never in my wildest dreams did I think that by calculating how much energy a capacitor has, I would be equipped to, at least in part, calculate how much energy light carries. That's insane if you ask me.
Lots of people have become used to tapping, swiping, and scrolling to access information and entertainment. But how do these everyday devices work? We can see touch screens everywhere. They've become a part of our everyday lives. We barely bat an eye while scrolling through Instagram or retweeting something on Twitter. But how does putting a finger on your phone's screen to perform these tasks actually work? Let's explore that in this video. Now, to begin with, we will look at the structure of a touchscreen display first, and then we will go into the physics of it and understand how does a phone actually recognize where are you touching the screen. It turns out that a touchscreen display is comprised of many layers. At the very top, we have the protective glass, which is chemically toughened. And smartphone glasses are over 5 times stronger than normal glass, and that's why the screen doesn't crack easily when you mistakenly drop it. We have the LCD screen at the bottom that produces the images that you see. And between the LCD screen and the toughened glass are several sheets. One of them, the top sheet, is a sheet containing a grid of hair-thin lines of a conductive metal, and this conductive metal could be indium, tin oxide, or copper. And I have shown them as colored, but these lines are transparent, and of course there are many of such conductive lines on the top sheet. Below that there is an insulating layer. This is an insulating layer which separates the conductive lines at the top from this sheet that also has hair thin lines of a conductive metal, but in a direction perpendicular to the first one. Let's look at the structure of the top sheet and the bottom sheet more closely now. Each of the rows of the top sheet, they also have a metal plate attached to them, and that is coated with a conductive material like copper or indium tin oxide. And similarly, each of the electrode in the bottom plate also has a metal plate attached to it. And there is a current flowing in the top sheet along these blue wires, these blue electrodes, as a result of which there is some positive charge that is deposited on all of these plates. And when these two sheets are placed on top of the other, they form a grid-like pattern which kind of looks like this. So we have this grid of tiny capacitors. Because there is a positive charge at the top plate, it induces a negative charge at the bottom plate of the capacitor, and with no external disturbance whatsoever, that charge is maintained constant by the phone's battery. Now over here you see around 35 capacitors, but on your phone screen you have around 1500 rows. So you can imagine the number of capacitors that are there on your touchscreen display. Now let's pick any one of these capacitors and look at it more closely. So we have the positive plate at the top and the negative plate at the bottom. Since there is charge on both of these plates, there are electrostatic field lines which go from the positive end to the negative end. And these fields aren't getting disturbed because there is nothing that is disturbing them. The phone's battery is maintaining a constant charge on both of the plates, and the electric field is also maintained with no disturbance whatsoever. But now comes the interesting part. Let's say we bring a conductive material like a finger, something conductive like a finger, close to one of this capacitor. Why don't you pause the video at this point and think about, will the presence of a conductive material like a finger, will it affect the electric field in any way, or will there be no effect? Pause the video and think about it. Alright, hopefully you have given this a thought. Now, human body is made about 60% water, and pure water is an insulator, but the water that is inside of us is impure. It is loaded with ions, atoms or molecules that have a net electric charge. And the presence of these charges changes or distorts the electrostatic field that was present between the capacitors. And now the field lines look like this. It is as if your finger is stealing away some of the electric field lines from the capacitor. Now the electric field strength has decreased slightly, and we know that electric field strength is equal to V by D, the potential difference between the plates divided by the separation between them. So if the electric field strength decreases, even the potential decreases. This drop in potential is detected by the sensor, and then the sensor pinpoints that particular location where the voltage has been dropped. And that is how basically a touchscreen display works. Now there are a couple of things that you might have experienced. Something like if there are water droplets on your touchscreen starts behaving very randomly as if you have touched at multiple locations on the screen. That is because presence of water distorts electric field at many of these capacitors, and the sensor detects all of those changes in the electrostatic field, sends that signal to the processor. So your phone ends up doing multiple things at once, maybe opening multiple apps all together. And on the other hand, if you're wearing gloves, you might have experienced that you aren't able to operate a touch screen. That is because the fabric of the glove is an insulator. So when you bring your finger close to the screen, there is no change in the electrostatic field and there is no voltage drop, and nothing is detected by the sensor. Now the touchscreen displays that are used these days, they do not really use this grid-like pattern that you see on the screen, because there are a couple of disadvantages which are associated with this. So one of them is that this pattern starts becoming visible because you have two layers on top of each other compared to one transparent layer which might do the job. Now you have another transparent layer beneath that. So the pattern starts becoming visible slightly, and that is not the goal. The goal is to make it completely transparent so that the images that are formed on the LCD are clearly visible. And secondly, the electric field is inconsistent. That is because you have these capacitors and the electric field is strongest in between these plates. And there are these spaces around and between the capacitors where the electric field is not as strong as it would have been between the plates of the capacitor. So when you bring your finger closer to a capacitor, there is not enough distortion of the electrostatic field and there is not enough drop in the voltage for the sensor to detect it. So there needs to be some change to the design of how the grid is formed. And turns out there is one grid that is followed these days. Let me make some space. That pattern is called a diamond pattern. Now over here, the plates are not on top of each other. They are shifted slightly. You can imagine that the top sheet has been shifted slightly to the right and the bottom sheet is where it is. So as a result of which, the plates are not on top of each other, but the plates kind of look like this. And there is an advantage to this, because now your electric field lines, which could look like this, your electric field lines are not localized or not concentrated in one particular space. They are more spread out in the space, so that when you bring your finger closer to the plates, you get a proper distortion of the electrostatic field, which is then detected by the sensor and the location is registered by the processor. So this is the technology that mostly is followed right now in touchscreen, and the basic principle still remains the same, which is that bringing in a conductive material closer to the capacitor changes the electrostatic field, which then lowers the potential, or there is a voltage drop that is detected by the sensor, and that particular location is pinpointed and registered. We use microphones most of the time. Microphones are in AirPods, earphones, even in your mobile phones. And also you might have seen singers or podcasters recording in a studio, singing or speaking to a microphone. Whether you are plucking, drumming, singing or speaking, microphone creates a high quality audio. But how do these microphones work? That is something that we will explore in this video. Alright, now there are different types of microphones, and one thing common in all of the microphones is that it takes in sound waves, which is also called a pressure wave. As it changes air pressure near its source, it takes in a pressure wave and changes it into electrical energy, something like a voltage signal. It is taking in variations in air pressure and changing it into electricity. All of the microphones do this, and there are many types of microphones. There is dynamic, electric, condenser. They carry out the same process but with different methods. Here we will look into how condenser microphones change audio signal to an electrical signal. Let's briefly talk about its structure first and then the physics of it. So here we have a condenser microphone, and inside of the microphone there is a metal ring. This is a metal ring with two metal plates attached at both the ends. One plate is called a diaphragm. This is a diaphragm. And the other that you cannot see here, it is on the other side. It is at the back. That is called a back plate. And these plates are mostly coated with gold because gold doesn't corrode. And this is how it looks like. Here you see the metal ring, and this is a diaphragm. On the other side there is a back plate, which is also a metal plate. Now let's look at a sectional view. Let's look at it from an angle. So for that, let me make some space first. Okay, here we have a mic, and here we have the metal ring at the top, and this right here is the diaphragm. This is the back plate, and both of the plates are connected to a battery. In between these plates there is an insulator, that is usually air, because air is an insulator. This setup now starts acting as a capacitor, because you have one positive plate and you have one negative plate, and there is an insulator, there is a dielectric between them. So this starts behaving like a capacitor. Now let's go back to the main process, the main function of a microphone. It converts one form of energy into another. Sound energy or variations in air pressure into electrical energy. How do we get electricity out of mechanical motion of air particles which produce sound? One thing that we can be certain of is that since the pressure of the air is varying, it is changing because of someone speaking into the mic, the final electrical signal that we are interested in should also vary and change, right? We know that a sound wave can be plotted, like you can plot pressure to distance, pressure versus distance, and the plot could look somewhat like this. We will have points of very high pressure, these are compressions, and you have points of negative pressure, which are rarefactions. So if the input audio signal is changing, the output electrical signal should also change, right? Other than this, you would also want the pitch of your voice to be the same, right? If someone has a heavy voice and they're speaking into the mic, when you hear your recording, you should be able to hear the same pitch, right? The pitch should match. And pitch is defined by the frequency. So that means the frequency of the electrical voltage signal should also be the same as the frequency of the sound wave coming in. We can increase the amplitude of the electrical signal later by running it across an amplifier, so we need not worry about the loudness for now. One thing that we can worry about is keeping the pitch same. So our voltage signal, electrical signal, should kind of mimic or copy the audio signal coming in. It should have the same frequency, and that means it will also vary just like the audio signal. Now the question is, how do we get the voltage changing? We know that if a capacitor is connected across a battery, it will start storing charge. There will be a plate with a positive charge. In this case, the back plate, this is the back plate. This will have a positive charge, and the diaphragm, the other plate, that will have a negative charge. And in some time it will get fully charged, because of which a potential will develop across the capacitor. So maybe if we change the voltage of the capacitor at a certain frequency which matches the frequency of the audio signal, maybe our job might be done then. Now, how can we change the voltage across the capacitor? We could change the amount of charge on these two plates and make the voltage change. But the voltage should mimic or copy the audio signal, right? It should have the same frequency at all times. How do we make the charge move instantaneously from one plate to other, exactly knowing the frequency of the coming sound so that we are able to change the voltage according to that? That seems difficult. That seems quite difficult. Instead of changing charge to change voltage, we can also change the capacitance itself, right? So what are the ways of doing that? Capacitance depends on just the physical characteristics of the plates. So it's area, the material between the plates, and also the distance between the plates. Changing the material in between or the area would be a difficult task, right? No one is getting inside a mic to do that all the time. We can, however, change the distance between the plates. And turns out that is what happens. The diaphragm, this diaphragm that you see, it is extremely thin. So thin that when the pressure wave, when the sound waves are coming in and when they strike it, it starts vibrating. When there is a compression, it is pushed inside, and when there is a rarefaction, it is kind of pulled outside. And how will that look? That could look somewhat like this. So let's say you have sound waves coming in from the left hand side, and when there is a compression, it pushes the diaphragm inside, and when there is a rarefaction, it pulls it outside. So constant sound waves coming in also vibrates the diaphragm according to that. When the diaphragm is pushed inside, the distance decreases, and we know that capacitance is epsilon naught A divided by D. So nothing in the top is changing, but D is decreasing, which means the capacitance should increase. Okay, so this is great because now we know that capacitance can change, and it can change totally mimicking or copying the audio signal. But we wanted a varying voltage, something that can be recorded. So if the capacitance is changing, then the voltage should also change, right? Because we know that Q, this is equal to C into V. There is one problem over here. If the capacitance increases, if this increases, then if there is just a capacitor and a battery in the circuit, the voltage across the capacitor will always be fixed. It is equal to the battery voltage. VB, this is equal to the voltage across the capacitor. VB is the battery voltage. So when the capacitance increases, more charge gets stored on the plates and there is no change in the voltage. So if we are somehow able to make the charge fixed on both of these plates, then changing the capacitance will lead to the change in voltage, right? So for that, what we can do is we can add a huge amount of resistance over here. Something around 1 giga ohms or mega ohms. So this resistor, it will keep the charge on the plates constant. There won't be any movement of charge. Now when the capacitor increases, the charge is fixed and the voltage decreases so that their product is equal to the fixed charge on the plates. This means that now VB, this is no longer equal to VC. It is no longer equal to VC because VC has decreased, right? If capacitance has increased, the potential across the capacitor has decreased. And if capacitance decreases, then the potential would increase. So if VC is decreasing, if it is decreasing, then there must be another voltage drop so that the addition is still equal to the battery voltage. And that is across the resistor. That is across the resistor. Then it becomes equal to the battery voltage. So for example, if let's say initially the voltage across the capacitor, which was equal to the battery voltage, and that was, let's say, 48 volts. When the capacitance has increased, some voltage decreased. So now let's say the voltage is 34, less than 48. So the extra voltage drop that is coming from the resistor. There is some voltage drop across this resistance, and in this case that would be 14 specifically. And similarly, if the capacitance decreased, then the voltage would increase. It would become more than 48, maybe 60. Then the voltage across the resistance would be minus 12. It would switch polarity. But their addition always comes out to be equal to the battery voltage. So as the capacitance oscillates with the same frequency as that of the sound wave, that leads to voltage change again with the same frequency. And this leads to a voltage drop across the resistor again with the same frequency, completely mimicking the input audio signal. And then this signal, finally, let's see how that looks like. This signal is read across a resistor that is then sent to the amplifier to increase the amplitude. And if there is a phase difference, that is also taken care of. Alright, so that is how a condenser, and it is usually called a capacitor, that is how a capacitor microphone changes audio energy into electrical energy using capacitors. Sound waves strike the thin diaphragm, changing the capacitance of the capacitor, which leads to a change in voltage that leads to a voltage drop across the resistor, which is then recorded and sent to other components in the circuit. We know that air is an insulator, right? Yet over here we see an electric spark in the air. Or if we talk about a bigger scale, we see lightning moving across the sky and many times also striking the surface of the earth. Still we see electricity moving through air. What is happening here? How is this possible? In this video we will explore how are these electric sparks created. Let's say we have a conducting metallic sphere and we give some negative charge to it. So this negative charge will get accumulated at the surface of the sphere, and let's say we keep on adding more and more negative charge to this sphere, so all the charge gets accumulated at the surface. Now we can't keep on adding charge to this sphere forever because something interesting happens. Not on the surface though, not on the surface of the sphere, but in the air around it. Air has many atoms. It has nitrogen, oxygen, some helium. So the atom that is closer to the surface of this sphere, all of the negative charge will repel the electrons of the neutral atom. And as a result, the shape could get slightly warped like this. You have all of these electron clouds slightly moving away. Now it is entirely possible that there is enough charge on this sphere so that it creates a strong enough electric field which can even strip this atom of one of its electrons. So as a result, you get an electron and an ion. Now this electron starts accelerating to the right because there is an electric field which forces the electron to do so. This electron collides with another neutral atom. And if it is going fast enough, it can knock an electron off the neutral atom, turning it into another ion. Now you have the original electron and you have one more electron that was knocked off from this atom. Two electrons are now accelerating and they collide with more atoms and they knock off more electrons, and then those collide further and knock off even more electrons, like a chain reaction. This creates an avalanche of electrons and ions. It's just as if we have a board at an incline with all of these balls held up by very thin rubber bands. So thin that you place one extra ball and the band will break. Now if you let one ball roll down from the top, you can imagine what would happen. This string will break, and then these balls would start rolling down and break this string, the bottom string, and now all of those balls are rolling down. Just how the electrons are behaving in this case. But one more thing, if you reduce the slope of this incline, if you make it flatter, if you reduce the slope, maybe this ball does not have enough velocity or enough kinetic energy so that when it strikes the balls that are held over here, maybe it doesn't break the rubber band. So there should be some slope to this board so that the ball has enough kinetic energy, enough velocity. Just like over here, the electric field should be strong enough so that it rips off an electron from an atom and gives it enough acceleration or kinetic energy to knock off other electrons from other atoms. Okay, so spark, where's the spark? If now I bring a sphere of zero potential, and let's say this is grounded, it is at a zero potential, there will be some positive charge that is induced on this sphere. As a result of the negative charge that is all accumulated over here, there is some positive charge induced, and there will be strong electric field lines from the positive end to the negative end. Finally, you get a region of space which is basically full of ions and electrons, and it is so loaded of these charged particles that it essentially becomes a conductor. A huge current goes between the two. This results in a spark. So that is how an electric spark is created. High charge warps the nearby atoms, stripping it away of one of its electron. You just need one, which then starts accelerating and colliding with other atoms, knocking off their electrons, and the same happens again. Eventually the space gets loaded with so many ions and electrons that the air essentially becomes a conductor, and electricity starts flowing and a spark is created. Now, there is an electric field magnitude at which the air becomes conductive, and the magnitude of that electric field is 3 into 10 to the power 6 volts per meters. So if there is a sphere of 1 centimeter radius, then we can find the maximum potential to which it can be raised to. We know that V, this is equal to ER. So if R is 1 centimeters, that means 0.01 meters. So the potential, this comes out to be equal to 3 into 10 to the power 4 volts, or 30,000 volts. So no amount of charging could raise the potential of a 1 centimeter conducting sphere in air more than 30,000 volts. If you attempt to raise it even more, if you try to increase the potential by adding extra charge, that would just cause the surrounding air, that would rip off the electrons from the atoms in the surrounding air, and that would lead to the formation of this spark. Each second, the sun produces 3.8 into 10 to the power 26 joules of energy. In this video, we will see that the sun is not nearly hot enough to be able to produce this much energy. It is too cold, so cold that it shouldn't be alive. Let's see why. Now, as we speak, protons are smashing into each other in the sun's core, releasing a huge amount of energy. This kind of reaction is called a nuclear fusion. Just like as if we had two water balloons approaching each other with some velocity, colliding, and in doing so releasing the water inside. In nuclear fusion, we can think of energy released as water over here. But we know that the two protons will repel each other because they have the same charge. They are both positively charged. So how can protons come close enough so that they fuse to release all this energy? We can take some hint from this analogy. Only if the balloons are approaching each other with sufficient velocity, they will burst open to release all that water. Similarly, the protons must have sufficiently high velocity to begin with. Only then they can overcome the Coulomb repulsive force and fuse. For high velocities, we would need high temperatures. The temperature of the core of the sun must be high enough. This can be expressed mathematically. We can write that the average Ke of all the particles in the sun's core, it is proportional to the temperature. And when we remove the proportionality, we get 3 by 2 into the Boltzmann constant Kb into the temperature. This is the average kinetic energy of the protons in the sun's core. It is directly related to the temperature of the core. And value of this Boltzmann constant, that is 1.38 into 10 to the power minus 23 joules per Kelvin. We are interested in the temperature of the sun's core. So let's keep temperature on one side and bring everything else on the other side. So this is what our equation becomes. If we know the kinetic energy of the protons, then we can figure out the temperature, right? Now, protons, they repel each other. As they come close, their velocity must decrease, which decreases their kinetic energy as well. At this point, why don't you pause the video and think about where is this kinetic energy going? Is it transforming into something? Is it not? Why don't you pause the video and give it a thought? All right. Naturally, if protons are just left to themselves, they would never want to approach each other. But when they are made to approach each other, in this case, because of high velocity, their potential energy must increase. So kinetic energy in this case is being transformed into the potential energy of the two protons. And according to conservation of energy principle, we can write that the total mechanical energy initially, when the protons were far apart, that is equal to the total mechanical energy finally, when the protons are close enough to fuse. We can expand this and write it in this manner. The total mechanical energy and initially and the total mechanical energy final. Here U is the potential energy, initial and final. Now initially we can assume that the protons are far apart and they are not interacting with each other in any way. So the initial UI, the initial electrostatic potential energy, is 0, considering that the protons are far apart and there is no interaction whatsoever. And final kinetic energy, that is also 0, because when protons are close enough, so close that they can fuse, they have lost all their velocity and they are about to go back, but they can't because they have come so close that they end up getting fused. So final Ke is also 0 and initial potential energy is 0. That gives us the initial kinetic energy of both the protons, that is equal to the potential energy, the electrostatic potential energy of the two protons. Now let's try to work this out and figure out the kinetic energy. So this is equal to the final potential energy, that is 1 by 4 pi epsilon naught, into the charges, that is Q1, Q2, divided by the distance between the center of the two protons. Now this is equal to 1 by 4 pi epsilon naught, and instead of this huge constant we can write 9 into 10 to the power 9 into Q1, Q2. Both of them are protons, so both of them are positively charged and they have the same charge, and that is 1.6 into 10 to the power minus 19 whole square, because you have Q1, Q2 here, divided by R, the distance between the centers, which should be 10 to the power minus 15 meters or 1 femtometer. Only if the protons are this close, they will be able to fuse and release energy. We can work this out, or we can just directly multiply this with 2 by 3 into Kb. That will give us the temperature of the sun's core. So multiplying this further with 2 by 3 Kb will give us the temperature, the final temperature of the sun's core. And I encourage you to pause the video and try out this entire calculation on your own. Alright, hopefully you have given this a try. The temperature that you should have arrived at is 1.1 into 10 to the power 10 kelvins. But now the real temperature of the sun's core is not this. It is much lower. It is 15 into 10 to the power 6 kelvins, or 15 million kelvins. It is much lower than what we arrived at. This temperature will not give enough velocity to the protons so that they can come closer and fuse. And that is why the sun should not be alive. But of course it is alive. How can that be? What is happening here? It turns out that classical physics, that is thermodynamics or Newton's laws, conservation of energy, they won't be able to explain all of this. But quantum physics does explain why the sun is alive. And it is quantum tunneling effect, which makes it possible for the protons to fuse even at a temperature of 15 million kelvins. Now we will not be going into how exactly quantum tunneling helps, but the amazing thing is that just sitting on a chair with a piece of paper and some knowledge of electrostatic potential energy and conservation of energy, we were able to predict the temperature of the sun's core and form a really sound argument on why the sun shouldn't be alive. Let's solve a couple of questions on combination of capacitors. For the first one, we have 4 5 microfarads capacitors which are combined as shown below. What is the equivalent capacitance of this combination? We need to report the answer in microfarads. As always, hit pause and try this question on your own first. Alright, hopefully you have given this a shot. Now before we get into figuring out the equivalent capacitance, first let's label all the nodes and all the capacitors. So we can call this C1, this is C2, C3 and C4. And we can label all the nodes as well. We can call this A, let's say this is B, this is C, D, and we can call this node as well. We can say this is E. Okay, now our strategy would be to identify sets of capacitors which are in series or parallel, because we know how to calculate the equivalent capacitance of those capacitors which are in series and parallel. So first, let's try and understand the potential difference across C1. Let's see what is the potential difference across all of these capacitors so that we know if they are in parallel. Now across C1, the potential difference across C1, that would be, so let's write C1 here. Across C1, the potential difference is VAB. This is VAB. Across C2, this would be VBC. But now if we look closely, if we look at the terminals, so we have the terminals XY, potential at E will be the same as the potential at A, because there is no circuit element in between, so there is no potential drop between A and E. Similarly, potential at E should be the same at potential at C. Again, there is no circuit element in between, so there should be no potential drop, which means we can write this: if VA is equal to VE and if VC is also equal to VE, then we can write that VA is really equal to VC. And if this is true, then VAB is really equal to VBC, because we can write either as in terms of the other. We can write VBC as in place of C, we can write A, and these two become equal. So turns out the potential difference across C1 and C2 is the same, which means that they are connected in parallel. Now let's look at the potential difference across C2 and C3. Across C2, we already know, we have written it, this is VPC, and across C3, it's VCD. Now when we look at the diagram, we see that the point B is connected to point D with this wire. Between points B and D, there is no potential drop. So VB should be equal to VD. There is no potential drop between them. And if VB is equal to VD, then in place of D, we can write this as VCB. So turns out the potential difference across C2 and C3 is also the same, VBC, or in terms of VCD. But that's the same, since there is no potential drop across B and D. It is connected by this wire which has no circuit element, so no potential drop. So C1, C2, C3, all of them are really connected in parallel, because the potential drop across each one of them is the same. So for C1, C2 and C3, we can find the equivalent capacitance by simply adding them, C1 plus C2 plus C3. Because if capacitors are connected in parallel, this is how you find the equivalent capacitance. And C4, in place of, now when we find the equivalent capacitance of C1, C2 and C3, we can replace all of that with just one capacitance. And then you have C4, which is connected in series. So the circuit looks like this. You have XY, these are the terminals, and then this is the equivalent capacitance of C1, C2 and C3, and then you have C4, which is connected to the equivalent capacitance. This right here is C4, and this right here is the equivalent capacitance of C1, C2 and C3. So equivalent capacitance of these three should be 15, because one is 5. This is 15 microfarads. And now this equivalent is connected in series with C4. So now we need to figure out the equivalent capacitance of these two. Then the relation for that, and I'm writing it on the top over here, it is 1 upon C final. I'm writing the final equivalent capacitance. This is equal to 1 upon C equivalent, which is this, that is 15, plus 1 upon C4, and that is 5. Now we need to work this out, so I would suggest you pause the video and work out this calculation. Here C equivalent is really 15 and C4 is 5. And when you work this out, you should get the final equivalent capacitance as 3.75 microfarads. Alright, let's look at one more question. Now here we have 6 3 microfarads capacitors which are combined as shown below, and they are connected across PQ. What is the equivalent capacitance C of this entire combination? Okay, like we did in the previous video, so we will start off by labeling all the capacitors. So let's call this C1, C2, this is C3, C4, and let's call this C5 and C6. And now let's label all the nodes that we see. So we can call this as A, B, let's call this C, and let's call this D. Okay, now again our approach would be to identify those sets of capacitors which are in series or parallel to each other, because we know how to calculate the equivalent capacitance for those sets of capacitors. So let's try and identify them in this combination. Now this is connected across PQ. We can start off by trying to understand the potential difference across each capacitor. So for C1, across C1, the potential difference really is VAB. We can say that is VAB. And across C4, it is C4, this is VAD. VAD. Okay, now the good thing is that the capacitors are of the same magnitude. It's 3 microfarads all throughout. So the amount of potential drop in this branch over here should be the same as the amount of potential drop in this branch over here. And that should mean that the potential at B should really be equal to the potential at D, because the amount of potential drop in this branch is the same as the amount of potential drop in this branch. So from VA, the potential starts dropping and it drops to the same value, drops by the same value, because the two capacitance are the same. So VB is really equal to VD. And what does that mean? That means that there is no current flowing, there is no charge flowing in this branch, the branch that has C5 and C6. So these two capacitors, they play no part, they play no role in the overall capacitors. They are not even the part of the circuit, because the potential across B and D, it's the same. So no current, no charge flows between B and D. So now the problem just has these 4 capacitors, C1, C2, C3 and C4. And with them, let's try and draw the new circuit. So the new circuit that would look like this. So we have C1, now we have C2, and these two are connected in parallel with C4 and C3, and then you have them connected to P and Q. So this is C1, this is C2, this is C4, and this is C3. Now these two are connected in series and these two are connected in series, and they themselves are connected in parallel with this combination C4 and C3. Now we can figure out the net capacitance. So for the top branch, the net capacitance would be, we need to find the equivalent capacitance for the top branch. That would be 1 by 3 plus 1 by 3. Similarly, for the bottom branch, it would be 1 by 3 plus 1 by 3. But this is 1 upon C equivalent. So when we find C equivalent, let's call this dash. This would be 3 by 2, that is 1.5. And similarly, C equivalent here, that would be 1.5. And you can take your time and work out this calculation. And now those two combinations are connected in parallel to each other. So now the circuit that we have is, we have this capacitance of 1.5, and they are connected to PQ. Here you have P, here you have Q. Okay, now this is 1.5 and this is 1.5. Now they are connected in parallel, and with parallel, the equivalent capacitance is figured out by adding the capacitors. So this is 1.5 plus 1.5, and that would be 3 microfarads. Alright, you can try more questions from this exercise in the lesson. And if you're watching on YouTube, do check out the exercise link which is added in the description. Let's solve a question on electric potential energy. The image below shows the electric field lines of a positive point charge. Consider the potential energy of the system UM or UN when a small negative charge is present at the point M or N. We need to choose the correct statement from the following. As always, hit pause, try this one on your own first. Alright, hopefully you thought about this. Now let's try to see what the question is trying to tell us. So we have a small negative charge, and this is present at the point M and N, and the potential energy when the charge is at N, that is UM, denoted by UM, and when the charge is at N, that is denoted by UN. So which one's bigger, UM or UN? Now to answer this, we should ask ourselves, when there is a small negative charge in the presence of a fixed big positive charge, where and why will the negative charge move? Now to answer that, we can say that it will move towards the positive charge. That is where it will move because of the electrostatic force of attraction. Opposite charges attract, and it's moving because there is a force of attraction. The positive charge has an electric field which goes away, it radiates outwards, and because the negative charge is present in that electric field, it experiences a force not in the direction of the electric field because it's a negative charge, in the opposite direction towards a positive charge. And finally, we can ask ourselves, when these two charges come closer to each other, what does that do to the potential energy of the system? Now to think about that, we can draw a parallel. We can think about a block or any ball which is dropped from a height and it goes rushing towards the earth because of the force of gravity. In that case, what do you think happens to the potential energy of the system? Well, turns out it decreases. The ball moved towards the earth, and the earth really does move, but it's just negligible because of the mass of the earth. So similarly, there is an attractive force here as well between the negative charge and the positive charge. So when you let them be, when you let go of the negative charge, it goes towards the positive charge, and in doing so, the potential energy of the system decreases. So if we have a negative charge which is kept at m or n, we can ask ourselves in which direction should the negative charge move so that the potential energy of the system, that is the positive and the negative charge, the potential energy of the system decreases. Let's try and make a tunnel. Let's say we have a tunnel over here, and the negative charge is only restricted to move between these 2 points. So if we leave a negative charge at point n, due to the electrostatic force of attraction, that negative charge will start moving towards point m, and that tells us that the only reason that the charge is moving from n to m is because doing such movement, going in that direction, is reducing or decreasing the overall potential energy of the system. So just by that logic, we can say that the potential energy at m, that must be less than the potential energy at n. But let's try and also answer this mathematically. So we can use the relation of potential energy, and we can take a positive charge. We can say this is plus q and minus q. So there are 2 charges. There's plus q and minus q. So potential energy at m, we can write this as this is equal to minus capital Q into small q divided by 4 pi epsilon naught into rm. We can say that is a distance, and potential energy at n, this is equal to minus capital Q into small q divided by 4 pi epsilon naught rn. Now we can see that rm is less than rn. So in the denominator, if we compare these two, if rm is less, potential energy at m, they should be more, and if rn is more, un should be less. But be cautious because these are negative numbers. So a higher negative number really is less than a lower negative numbers. Think about this, like minus 50 is less than minus 30. Similarly, a higher negative number, that is um, is less than a lower negative number. Now we can also draw a graph and try and make sense of it further. So if we draw a potential energy distance graph, the curve looks like this. You have u and r, u versus r. So what this really means is that the point m, let's say point m is over here, point n is over here. We know that rm is less than rn, r is greater. So the potential energy at m, that really is this value. This is um, and the potential energy at n, that is really this value. Even from the potential energy distance graph, we can see that that is really less than un. So it turns out minus un should be negative, and the answer is option B. Let's look at one more question, and that will be on work done. So here it is. Okay, the image below shows the electric field lines of a positive point charge. Here it is. These are the electric field lines. The work done by an external agent in slowly bringing a small negative charge. Okay, this one's negative. And in brackets, it's written 0 acceleration from infinity to the point x is w. Choose the correct statement about this work. Is it positive, negative, or is it 0? Alright, let's think about it. So a charge is being brought from infinity to this point x, and it is brought with 0 acceleration. What is 0 acceleration? Well, we know from Newton's laws, all the way back to Newton's laws, that when the net force on any object, when it is 0, then that object is moving with 0 acceleration. There is no acceleration with which the object is moving. So is the net force on this negative charge 0 really? Let's think about the forces that are acting on this negative charge. So this is the negative charge, positive charge. There must be an electrostatic force of attraction. So that force is directed towards the center. Let me draw that over here itself. This force is directed towards the center. Let's say this is Fe. And now if there is a force directed towards the center, but someone is bringing a charge from infinity to this point with 0 acceleration, so there must be a force that is balancing this electrostatic force of attraction, and that must be in the opposite direction. must be in the opposite direction like this. We can call this F external. An external agent is doing this work. Now, in order to move the negative charge from infinity to a point X with zero acceleration, this F external must always be in the direction opposite to the electrostatic force of attraction, because this will be always directed towards the center. And we also know that the charge is being brought from infinity to this point, so the displacement really is in this direction. This is the direction of displacement. So this force external and displacement, they are in the opposite directions. And from work done, we know that work done is F dot D. This is F D cos theta. Theta here would be 180 degrees because displacement and force external, they are in opposite directions. Cos 180, that is -1. So work done by external agent, this really is less than 0. It's a negative value. Alright, you can try more questions from this exercise in the lesson. And if you're watching on YouTube, do check out the exercise link which is added in the description.